So essentially there can be two effects of dark matter neutrino interaction in cosmology, and this is more or less the scheme. This is the standard scheme, but let me just try to, once again for completion, let me try to elaborate on that. So what we will try to do is that now we have neutrinos and we have dark matter and they are interacting. So their conservation equations are modified due to the interaction term, and then we have power derivation equations. The usual power derivations are standard density power derivation and velocity power derivation equation for dark matter, but here on top of that we are considering that neutrinos can not only interact with dark matter, that can also take part in power derivation. So on top of those two equations we have two more equations, one coming for neutrino density power derivation and another one is for neutrino velocity power derivations. So using all these things we can modify the publicly available code class, and we can try to find out the effects on CMB/TT as well as matter power spectrum, and then we can do the standard parameter estimation using MCMC and try to find out what can be the possible constraints on those extra parameters and if there is at all any reflection on the standard 6 parameter description. So here in this framework we have this 6 parameter. On top of that we can consider two things. One is coming from U and the other one is from gamma, and if we consider sum over neutrino mass as a parameter, which I will do later on, we have another extra parameter. So these are the set of parameters I have right now. So this is the standard power derivation equation. As you know, I am not going into details of all these things, but as I said, these are the two power derivation equations for density and velocity power derivation with dark matter fluctuations alone. If we consider that the neutrino is also taking part in perturbations and also dark matter and neutrino are interacting, then these equations are modified to this. Where the red and blue, they are the correction terms coming out of these extra interactions. So these are the standard density and velocity power derivation interaction equations. You can find out the effects of this dark matter neutrino interaction on the right hand side. All these red terms, they are coming from dark matter annihilation, and blue terms are coming from dark matter neutrino scattering. On top of that we have this density and velocity power derivation equation for neutrinos as well, which goes by this. And as I already pointed out, all these effects, the blue effects, dark matter neutrino scattering, they are summarized through this parameter U, and the annihilation part is summarized through the parameter gamma. So that's the summary part. On top of 6 parameters we have 2 parameters right now. I am not considering sum over neutrino mass. I will come back to that later on. And these are theoretical plots, of course. What can be the possible effects of dark matter neutrino scattering on CMB/TT power spectrum and matter power spectrum? As you can see that if you consider the interaction term to be non-zero, this is the lambda CDM part where interaction term is 0, but if you consider them to be non-zero, then there is enhanced CMB/TT power spectrum, some of the peaks are enhanced, and for matter power spectrum that is suppressed for sure. Same is true for dark matter annihilation, albeit the fact that the effects are relatively small compared to dark matter neutrino scattering. So now this is the real business. So what we have done is that, of course, once again let me repeat, we have taken the standard 6 parameters. On top of that we have taken 2 extra parameters, one is U and the other one is gamma, and we have tried to run MCMC and we have tried to constrain all the cosmological parameters using the full CMB, and this is what we got. So basically this is the U parameter and this is the gamma parameter. As you can see that they give rise to a non-zero regime, but 0 is not excluded. So essentially this will give you much more better picture of that thing. So what you get is that best fit value is still 0. So there is no compelling reason why you should consider dark matter neutrino interaction at the first place, at least from the latest CMB data. But if you consider that, then you will have a very tight bound on interaction term. So from CMB alone, from Planck 18, you get a constraint of U which is less than 10 power minus 4, but that includes 0 as well. And similar results can be found out using ACT and SPT as well, and the results are not expected to vary much from there. Okay, so with this, let me try to find out some future prospects of this. And 2 future prospects I will discuss, as I said, reionization and post-ionization era. I don't have much time, so let me try to go a little bit fast. This work once again was done by Arnob and Antara, who is a postdoc at IOP right now. So what we have done is that using all these constraints coming from latest data, we tried to find out, we tried to generate the, or rather the in-body simulation code and generate the H1 maps and try to find out if there is any possible signature for that, so far as the future CMB, future 21 centimeter emission SK1 low is concerned. So this is a very simple kind of thing. We tried to restrict ourselves to the simplest tan-H reionization model, and we tried to assume that around Z equals 8, 50% ionization condition is satisfied. But of course, we have two astrophysical parameters and a huge uncertainty is there. One is the anion and the other one is XH1. XH1 gives you the 50% ionization condition, which remains pretty close to 0.5 at z equals 8. But anion can vary from 23.21, this is for lambda CDM, to 500. So we ran all these things, and what we found out is that these are more or less the constraints on dark matter neutrino interaction from future 21 centimeter emission without considering any particular instrumental specifications as such. And this is the non-trivial effect on the power spectrum as well. So essentially, increase in U actually suppresses the power and hence generates a lesser number of dark matter halo and less ionizing radiation. And this is the output for H1 maps at z equals 8, as I said. In the next work that we have been doing with Kumon and et al. So we have made n number of realizations of that for different redshifts. So, but this is the simplest structure. What we found out is that this first one is for lambda CDM, where interaction is 0, and then rest of the things are following. So essentially, as you increase the dark matter neutrino interaction, it delays reionizations. You have to make that up by increasing the anion. Up to anion 500 is allowed. So essentially, up to this value of interaction is allowed. So we found out that U is less than 10 power minus 4 from CMB and from CMB alone. But here, for reionization conditions, if we consider 50% ionization at z equals 8, then you get tighter constraints, which is of the order of 10 power minus 7. And these are, of course, we tried to find out the detection prospects in SQ1 low. This is the signal power spectrum, this is the noise power spectrum, and what I found out is that for this scale at least, the SNR is greater than 5. So essentially, you get tighter constraints on dark matter neutrino interaction, which is this, and prospects of detection in SQ1 low is relatively high. So let me move on to the next work. I don't have much time in hand. So this work is once again done in same collaboration. So what we did previously is that we couldn't run any MCMC for that because these astrophysical parameters, lots of uncertainties are there. So we didn't want to incorporate those uncertainties into the analysis. For that, what we did is that we tried to move forward and we considered in this case the total neutrino mass for the first time, and then we took help of the post-reionization and galaxy surface, and we ran this code. So this is the MCMC output for SK1, different combinations of that, SK1, SK2 and Euclid, and you can find out that this is the constraints on the neutrino interaction, and this is the M total over here, sum over neutrino mass. So this is the summary plot. We tried with other missions as well, all the future CMB missions, Lightbird and etc., all the other combinations, and essentially this is what we get. We get that future mission SK2 will be able to put even tighter constraints, which is of the order of 10 power minus 8, and a difference and the error in estimation of total neutrino mass, which is of the order of this. But as expected, H0, S8 and all the other parameters, they remain more or less close to Planck value. Because I have 2 minutes? Okay, great. So I'll touch upon the next work. So this work is, I mean, if we consider any non-trivial effect of neutrino interaction, it can be self-interaction, it can be any other thing. And this work was done in collaboration with Rikmoy Shamanta, which is a faculty at BET Switzerland, and my student Saurabh Pal, which is sitting over here. So let me try to go over this little bit. Neutrinos can interact with themselves or with others. The flavor changes can also be taken care of, but it has been found out that the effects are really small, so we are not considering that. And that can interact at early time, also at late time. So for early time, it can happen due to 4 Fermi weak interaction, and for late time, there can be different possible sources like neutrino decay, self interactions, and neutrinophilic interactions, so on and so forth. In general, in a model independent way, the neutrino interaction can be parameterized like this. This is available in the literature. With different values for interaction, you can put it either in the early universe regime or in the late universe regime. And you can try to constrain the free streaming window of neutrino, which is like this, okay, using CMB and galaxy full zip. So what we have done in our work is that we concentrated mostly on early universe neutrino interaction. And this is what we found out for different values of n, as we found out 3, 4 and 5. 5 is more interesting for some reason, I will come back to that later on. For n equals 3, these are the constraints. So now we have the standard parameters. On top of that, we have the free streaming redshift as well as sum over neutrino mass, and as well as this nnt is fixed over here. So these are the constraints we found out for n t equals 3. Second one is for n in t equals 4. I will try to concentrate on the last one. Because as it can be shown, this particular case can be mapped into self-interacting neutrino. And people are trying to constrain self-interacting neutrino or effect of that on different cosmological observations. So this is what we found out for self-interacting neutrino. Hubble parameter remains pretty close to Planck value, and the sum of our neutrino mass is this much from Planck alone, whereas if you include Planck with the galaxy full shape, then this is little bit relaxed. So if you include these things, self-interacting neutrino, then this can be the possible constraints on sum over neutrino mass. And of course, instead of Planck 18, if you make use of ACT, then the results are slightly different. And these are the future prospects. We have tried to forecast on the future CMB mission, future galaxy survey, Euclid as well on top of this, and this is what we found out. Once again, H0 remains pretty close to Planck value, but the constraints are much more improved, the error bars are less, and sum of a neutrino mass is slightly improved than the standard scenario. So this is the state of the art scenario right now. Because I don't have any more time, I will stop over here because this has been already discussed by Shorav. So this is the final slide, which is my favorite cartoon from one of the poets, Bengali poet, Sukumar Rao. It always tells us that yes, it's good to fight and debate, but at the end of the day, it's good to shake hands. And let's do hope that all these cosmological and particle physics observations, they will be able to shake hands at some, maybe in near or distant future. Thank you so much.
Thanks, Supratik, and also for keeping in time. Questions? Yes.
What are the implications for the constraints on N effective when you include interactions?
Right. Thank you so much. This is a very nice question. We tried with N effective and we found that there is no such improvement or there is no change as such with these things.
Standard delta N effective your quote remains.
Right. So we didn't try to put our life complicated.
In all the interactions you have examined?
More or less. Sum of a neutrino mass is something that is getting affected.
Okay, thank you.
So you showed us here.
Yes,
you showed a slide where if you add Planck plus full shape, the constraints on the total neutrino mass degrades.
Yes.
How is that possible? If you
yes,
add information,
so probably this one, right?
Yeah.
No, you have some extra parameters, and that because here we are considering this interaction as well. If you don't have interaction, then it's absolutely fine.
Okay.
But because you have interaction term, and that basically drags the other parameters, and essentially this is what you get. I understand your doubt for sure. Yeah, that should not be the case, but essentially what we are also investigating this one. But our take on this is that because this extra parameter is there, which is actually dragging the value and putting it relatively.
Hi.
Yes,
here.
please.
Thanks for the very nice talk. So for the neutrino self-interaction thing, did you, probably I missed it, did you consider two different power laws for the wedge redshift?
No,
or
not
just
really.
one?
One power. This is the simplest scenario as I pointed out. Thank you very much. This is the standard model independent scenario. Okay? And we took different values for n in t. For the value which is in int equals 5, that can boil down to particular neutrino self-interaction model. For the rest of the things, that may not be neutrino self-interaction at all. And we did not consider any different power law scenario for different cases.
I see. So 3, 4,
So that's pretty simplified scenario.
3, 4, they are just some, like, as just phenomenological parameters.
Right, absolutely.
Thank you.
You can map, some of them you can map to standard particle physics scenario, but some of them you cannot. But definitely, that will be a very interesting thing to explore further. Thank you.
Can you explain where 3, 4, 5 come from? Because they can't be arbitrary. You have
Definitely.
particular physics model,
Definitely.
light mediator, IV mediator, it gives you a particular
Absolutely.
value.
Thank you so much. So, yes, so this is the generic prescription, and as I have shown, this 5 comes from neutrino self-interaction. For other cases, it can be interaction of neutrino with other cosmic species. It may not be neutrino as well, like the present scenario, like the previous scenario I have discussed, dark matter neutrino interaction. So there we did not consider any particular kind of parameterization. There we started from the first base that dark matter and neutrino are interacting, and interaction can come from particle physics scenario, like it can be
What mediator you choose define the
absolutely.
Which was temperature independent in that case?
Right. Absolutely.
That already fixes what mediator you have.
Absolutely.
Different mediators can give you different
Right. People have explored this scenario, which one can be mapped to which one, but I cannot remember all of them, to be very honest.
One quick question. The H1 map at redshift 8 that you showed, there were 3 different scenarios that you showed, but all the 3 seem to produce maps that look almost indistinguishable. So is there going to be, even with SK, a possibility of actually...
Right. Good question once again. Good question once again. Because of the simple fact that the change from lambda CDM is really, really small. Okay, that's a very interesting thing, and that's why we are doing this along with Sumon and Leon. We are doing a follow-up exercise of that. So we did not concentrate only on Z equals 8, but for the entire redshift regime of reionization. Okay, and we are trying to do large cluster statistics from there, and we are trying to see what can be the possible consequences, for sure.
Hey, thanks for the nice talk. So in the first part of the talk, you talked about dark matter annihilating to neutrinos, and you also use Sommerfeld enhancement. So do you use data from neutrino telescopes which will probe these?
No, not really, thank you. And we found out the effects are really small.
No, but the neutrino telescope effects will be strong.
Right.
I mean, for sure.
Okay, thank you so much. So,
come in the power spectrum, come in the neutrino.
So I'll come back to you on that, and maybe you can discuss.
Thanks.
So I had actually 2 questions. So one is, are you considering, so you said that the parameter space is available in the particle physics, but is it available for all the flavors? Are you considering flavor dependence in the interactions? And if we get a signature of that something, so we have these rare meson decays. So for only tau neutrino will have some interaction space which is available. So in that case, can we say that we have some sensitivity to the flavor in case of cosmology?
Good question. I already pointed that out very briefly. People have tried considering different flavors and tried to find out what can be the possible constraints. Okay, and it has been found out that the flavors are not yet more sensitive to present CMB observations. So in our analysis, we tried to keep our life simple. We did not consider flavor. But the flavor changing neutrinos, people have tried with, say, different combinations like Planck and ACT, and tried to find out what can be. Even future forecasts with, say, CMBS4 is now obsolete for sure, but maybe in other observations, Lightbard and yeah.
Yeah, I have this kind of a general question. Let's say I have this information in CMB, and I know that fixed parameter lambda CDM fits very well, fine. Now, is there any limit that the amount of information available in, let's say, Planck CMB data, that I can start complicating my model and I can get any information extracted from there, or like I can get some limit to that?
Good question. Once again, so far as I know, once again, maybe we had a little bit of discussion on that. Very recently, Komatsu et al. They have written a paper where they have tried to find out what can be the minimum number of parameters that are required to constrain CMB in a completely model independent way using machine learning. And that turns out to be more or less, if you don't include polarization, it turns out to be 5 because of this degeneracy between AS and tau, and if you include polarization, that maybe that will turn out to be 6. So there is no compelling reason from CMB data alone why we should go beyond that. But because we have got only one universe, that should evolve from CMB2 today, we have other observations. On top of that, we are considering the cosmic entities which have particle physics origin as well. So people are trying to find out if there is some signatures in particle physics, what can be the possible signatures over here as well. So that's the basic motivation over here, but there is no compelling reason for sure. And that's why we get 0 value over here as well.
All right, let's move on. So let's thank
you so much.
once again. Next speaker is Suratna Das, and she'll be talking about some novel and attractive features of warm mutation. I'll give you warning at 5 minutes. Okay. It's 17 plus 3. So
Okay.
I'll give you warning at 12 minutes and then another warning.
Good morning, everybody. Let me first thank the organizers for inviting me to present my work in this conference. So I actually have been giving this talk of late in several conferences with overlapping participants. So if you are hearing this talk for the second time, or for the third time or for the nth number of times. So it's my apologies. Okay. So today I will be talking about warm inflation. This is a variant scenario of the standard inflationary model, and I will explain what warm inflation is, and I will tell you that this warm inflation has some very novel and attractive features over the standard inflationary picture that people do talk about in general. Okay. So of course cosmic inflation, as you know, is a very brief period of the early universe when the universe had expanded exponentially, and the dynamics is definitely governed by Einstein's field equations, where this is the Einstein tensor and this is the matter which determines the evolution of this space-time. And during inflation, this FRW metric has this scale factor sitting here, which is almost exponential, which is, oops, I went really far. Okay. So this scale factor is exponential. Oh, the scale factor is exponential here, and this is almost, this Hubble parameter is almost constant, and it depends very slightly on time. And on the right hand side, so what is the matter which can drive this universe, to expand exponentially, is a slowly rolling scalar field, and this is very much needed because, as I will explain in my later slides, that if you have such a very flat potential where the inflaton field is rolling over this flat region, only then you can drive this universe to expand exponentially and accelerate at that time. And at some point of time inflation has to end, and the standard Big Bang evolution of the universe should start. So what happens that at some point of time this flat region should end and the inflaton field should start rolling faster, so that inflation can end. But the thing is that, as because the universe is expanding exponentially during inflation, when inflation ends, we are having a universe which is devoid of all matters and everything. So you have to reheat a universe. How to reheat a universe? The standard picture is that the inflaton potential has this kind of a bottom of the potential where the inflaton field oscillates and reheats. Okay. So this is the standard picture of inflationary scenario, and the flatness of this potential during inflation is measured by the slow roll parameters. As you can see, this epsilon is proportional to the first derivative of the potential and eta is proportional to the second derivative of the potential, and both has to be much smaller than 1, indicating that this region has to be very, very flat. Okay. So I will come back to this picture again when I will be talking about warm inflation, and I will show you that this kind of a scenario is actually not needed in warm inflation at all, and that is one of the novel features of. So you can see that basically you need a very constrained kind of a inflaton potential to have inflation. Okay. So you cannot have any potential which can drive inflation in a standard picture. Okay. Now let me talk about slightly about what is warm inflation. So this warm inflation is something, so I already explained this picture for the standard inflation, which from henceforward I will keep mentioning as cold inflation. So as I said that in cold inflation you should have a flat region where inflation takes place, and when the potential becomes steep, inflation ends, and at the bottom of the potential the inflaton oscillates and reheats the universe. And this is the equation of motion of inflaton field during cosmic inflation, and this is basically nothing but a Klein-Gordon equation, except there is this factor sitting here which is coming due to the background expansion of the universe. This acts like a friction term in the Klein-Gordon equation, the general Klein-Gordon equation that people are used to seeing in particle physics. Okay. So this is a standard picture, but what is warm inflation? The warm inflation is saying that in cold inflation, basically this is a single field scenario where this inflaton field has no interactions and it's basically slowly rolling down its potential and expanding the universe. But in warm inflation, it is considered that this inflaton field has very strong interactions with other particles, so that this inflaton field can keep on dissipating its energy to a constant radiation bath and can maintain a constant radiation bath despite the exponential expansion of the background universe. Okay. So, what is happening is that in cold inflation, when you have to reheat the universe, you actually need some kind of coupling of the inflaton field with matter, so that it can dissipate its energy to the radiation bath. But while you are inflating the universe, you are ignoring all these couplings. But in warm inflation, you are not ignoring these couplings at all during inflation, you keep them effective, and you keep, so basically it is reheating throughout. Okay. So, when inflation ends, you actually have a constant radiation bath which can start a radiation dominated epoch, and so you do not need a separate reheating phase. So, basically this kind of a potential where there should be a bottom of the potential where the inflaton should oscillate and reheat, that is not needed in warm inflation at all. Okay. And again, you actually do not need a very flat potential, even a very steep potential can be sustained in warm inflation. Okay. So, also the equation of motion is changed. Now you have, so this is the dissipative term. So, this is the term which is taking away energy and dumping into a radiation bath, which is coexisting during inflation. So, you can see this dissipative term also includes another friction term in the Klein-Gordon equation of motion. So, now you warm inflation, you have two kinds of friction term, one coming from the expansion of the background universe and one is coming from the dissipative term. So, depending on which of these two dissipative terms are dominating the evolution of the inflaton field, one can categorize warm inflation into two categories. If this friction term is much smaller than the background friction term, then basically it is almost like a standard cold inflationary scenario, though you have a radiation bath maintained, but those kind of inflationary, warm inflationary scenario is called weak dissipative models, and when this part dominates over this part, then of course the dynamics is quite different from the standard cold inflationary scenario, and you call that warm inflation is happening in a strong dissipative regime. Okay. So, this is what is different between the standard cold inflationary picture and warm inflationary picture. So, why should we talk about warm inflation? First of all, as I already told you that warm inflation does not require a reheating phase. Okay. So, reheating is something which people are still struggling to understand, mainly because reheating does not leave much imprint on the CMB. Okay. So, we do not know what kind of reheating process that universe has gone through if you believe in the standard cold inflationary picture, but warm inflation does not require that kind of a reheating phase. So, that is one of the good point about warm inflation. The other thing is that the tensor spectrum is much more suppressed. It comes out to be when you do the perturbation analysis, the tensor spectrum is much more suppressed than in cold inflation. So, the standard lambda phi fourth or lambda phi, m square phi square kind of potential, which are generally ruled out in warm in standard cold inflation by the Planck data, you can make them accommodate in warm inflation, that because in warm inflation this kind of potentials does not produce that amount of tensor fluctuations. Okay. And there are other good reasons to consider warm inflation. First of all, in strong dissipative regime, it prefers small field inflation models, and we know that the present data prefer small field models. And warm inflation significantly elevates, if you try to build a supergravity model of inflation, then warm inflation can significantly alleviate the eta problem and gravitino problem. And of course, in 2018 and 19 there was quite a ruckus about swampland conjectures, and I showed that having warm inflation rather than cold inflation, it will help you get rid of the swampland conjectures and can have successfully inflation, one can embed inflation successfully in string models. So, I had written some series of paper on this topic, but I am not going to talk about this here today. But just look at, just to give you an idea of where warm inflation stands today, this is the standard cold inflationary picture which was first proposed by Alan Guth. If you read this, that this line at least, so of course inflation was introduced to get rid of these fine tuning problems of the Big Bang universe, but then this Guth is writing that these problems would disappear if in its early history the universe supercooled to temperature 28 or more orders of magnitude below the critical temperature for some phase transition. So that is when if you have a standard inflationary picture, when inflation ends, you actually end up in a supercooled inflation. Okay? So this is the standard picture, and you can look at its citation. So this is not the standard citation, I mean this is not a full citation. People when write inflationary papers nowadays, they don't even cite this paper. So the citation should be much higher, but this graph is very interesting. So you can see the interest in inflation is actually ever growing. So nowadays people are writing nearly 500 papers per year, which is a good thing. So this is even after 40 years of its proposal, this is a very active field of research. On the other hand, if you look at warm inflation, and if you read, first of all, read this abstract, so it is Berera who proposed warm inflation after 15 years where, when cold inflation was proposed by Guth. So it is written that assuming a first order phase transition during inflation, a model scenario is described which does not require a tiny coupling of the inflaton field. Thermal equilibrium is closely maintained and no large scale reheating is necessary. So this is, so this is the standard picture, but look at the citation. So it, first of all, it is orders of magnitude less, but it also tells you that warm inflation is very less explored than the cold inflationary picture. And if you look at this graph, the inflation is, the interest in warm inflation is also growing with time. So if not hundreds of papers, but at least 50 papers per year is being written in warm inflation nowadays. Okay. So today's topic is how inflation ends. So I am going to talk about this graceful exit. So and that's very important because you have to end inflation, and that is a very interesting in warm inflation. So this is a dynamics. This is the Klein-Gordon, this is the Friedman equations in standard cosmology, and you know if you have to accelerate universe, then you have to have a fluid with omega less than -1/3. So cosmological constant which has a omega -1 is a perfectly nice fluid which can give you exponential expansion, but the problem with cosmological constant is you will never get a graceful exit. On the other hand, if you have an inflaton field and let it slow roll means the potential energy has to dominate. So if you let kinetic energy dominate, then it will give you a steep matter which will not inflate the universe. On the other hand, if you let this gradient term dominate, it will give you a matter with negative equation of state, but not enough to inflate. But if you let the potential dominate, it will definitely inflate, it will behave like a cosmological constant. But the good part is that this potential, when the inflaton field is slowly rolling over it, this equation state will evolve, and at some point of time it will become positive, and that time inflation end and you will achieve graceful exit. And of course you need epsilon v to be much smaller than 1. And so this is the kind of epsilon that you need to end inflation in the standard cold inflationary picture, that it should be growing with time. So you need epsilon which is growing in time. So n is just number of e-folds, is the one way of keeping time in exponential order. So it's just treated as time. So you basically, so at this point your gradient is much more steeper, so it will become, it will remain smaller in this region, and at some point of time it will grow and end inflation. So this is a very mundane way of ending cold inflation, and you need a very specific kind of potential also. On the other hand, warm inflation is very different. Warm inflation takes place when epsilon is much smaller than 1 plus q. Q is this ratio of these two dissipative term that was present in the inflaton equation of motion, and you can see that now the condition of having ending inflation is epsilon v is not equal to 1 but 1 plus q. Both epsilon v and q evolves in time. You can basically derive this equation with if you consider this kind of a dissipative term, and it's very easy to calculate, and you can see now both these two parameters is evolving in time. So in how many ways you can achieve graceful exit in warm inflation? First of all, if you have a potential in which epsilon grows, in cold inflation you will always achieve a graceful exit in this kind of potential. So let first say if you have a warm inflation where Q is constant, then definitely this is like cold inflation, but you are raising the bar from 1 to 1 plus Q, and cold inflation will definitely end. On the other hand, if you have a warm inflation model where Q is decreasing, then also you will end warm inflation. On the other hand, if you let Q grow but with a smaller rate, then also you can exit warm inflation. On the other hand, if you let Q to grow faster than epsilon, so even if you have a potential in which epsilon grows, in which cold inflation will always end, you will not achieve warm graceful exit in warm inflation. So this is very interesting. Let's say if you have a potential where epsilon is constant, this is a classic case of this power law potential where epsilon remains constant, and you can never achieve graceful exit in cold inflation, but in warm inflation you can achieve this graceful exit if you have Q decreasing. So graceful exit in power law inflation is possible in warm inflation, which is not possible in cold inflation, and if you combine this this power law potential with this kind of epsilon, you will reach this kind of a scenario, okay, where you can gracefully exit from warm inflation. And if you have epsilon decreasing, then definitely cold inflation will never end, but warm inflation will end if you choose a model such that your Q is decreasing faster than your epsilon. Okay. So these are very different ways of ending warm inflation. So these graceful exit conditions put constraint on the combination of the inflaton potential and the epsilon that you can combine in warm inflation. So as you can see that even if you have, let's say your C is 0 and P is minus 1, so epsilon is 1 upon T. So if P is minus 1, then you can see that lambda phi 4 is not a good potential, because these white regions are where there is no graceful exit. So there won't be any graceful exit in this region. Okay. So this definitely gives you a constraint on what kind of potential you can have, but I don't have time to get into this, so let me skip it. So what I wanted to say that this background analysis of warm inflation is not a mundane task like in cold inflation, but it reveals the nature of the warm inflationary model itself, and it will give you constraint what kind of, even before you go and do your perturbation analysis, it will give you some hint what kind of potential goes with what kind of dissipative coefficient. So thank you.
Thanks, Ratna. Questions? Yeah, Razu.
Yeah, so thank you for the nice talk. So I think in the case of slow inflation, there was a fine-tuning problem from the viewpoint of effective field theory about the potential slow parameters. So do you have similar fine-tuning problem?
Fine-tuning problem in the sense that
so there
are thermal corrections to the potential.
Quantum correction to the potential usually.
Yes, yes. So there are people have constructed warm inflationary models where the thermal corrections are very less, the quantum corrections to the potential are very less, and also you do not need a very flat potential to drive inflation. Even
yeah, but I have been always wondering is the universe is expanding rapidly.
Yes.
And you have to heat up. So
yes.
If you heat up too much, universe becomes too hot, and if you heat up
no,
too
so
less,
the radiation fluid will always remain subdominant. Okay. So if it dominates, then suddenly it will become radiation dominated. But for 60 folds, at least you need to have your radiation fluid to be subdominant.
Yeah. So my question is whether you are tuning like the tuning there.
No,
or
it's not a fine tuning problem.
But well, I still
because see, if you have
we can discuss later.
Even maintaining a this subdominant radiation fluid, you have to dissipate a lot, right? Because the radiation fluid is always diluting away with an exponential rate, and you have to keep on pumping energy to the radiation fluid so that you can maintain a radiation fluid, right? Unless and until your potential is your potential energy is decreasing, you will not have a graceful exit, or you will not have a radiation domination at some point of time. Okay? So when this condition is met, epsilon v is equal to 1 plus q, you will also see that your potential energy is falling over your radiation energy density, and at this point your radiation energy density will tends to take over.
Yeah, thank you. Please discuss with me later.
Okay, I have one comment and two questions. You referred to the sociological aspects of citations regarding cold and warm inflation. That's the comment, and I have a follow-up question. Is that one of the challenges I face in understanding warm inflation is how do I calculate the spectrum?
Yes.
I do not know personally of a very clear place where the spectrum is derived very unambiguously.
Yes.
And conceptually, I see there is a radiation involved.
Yes.
There is another fluid involved. There will be, for instance, isocurvature perturbation in some simple, even in the simplest of cases.
Yes.
I haven't seen a clear discussion of what happens to the isocurvature perturbation. So these are the personal challenges I face in considering warm inflation.
Yes. So the thing is that as I showed you, the citation is very less. That means the field is very less explored. People haven't calculated isocurvature perturbation. There have been, now they have done the perturbation equations correctly, and there are review papers, and we are also organizing a school and a conference next year. All you people are all welcome to come to Ashoka University, where there will be lectures on warm inflation perturbation theory.
It's an open issue, and it's not resolved.
And there is a lot of thing that needs to be done.
Okay, so the second remark is is related to what Kazu asked. I don't know what he exactly refers to as a fine-tuning problem, but whenever I have turned on the gamma, and if you integrate your background equations, you will find that it is true that the radiation will be subdominant, but the energy density in radiation will jump significantly as soon as you turn on. So you start with some very small values. Maybe this is, I presume, the fine-tuning is referring to. At least the range of gammas I've explored, it jumps. It remains subdominant to the inflaton, but I see that in other words, the transfer of energy from the inflaton to radiation is significant, and the radiation acquires significant amount of energy even during the late stages of inflation.
We can discuss this later, but I have numerically evaluated all these background equations, but I have never come across this. I've never found
it will be subdominant, but substantial.
But substantial, of course. That is the difference between cold inflation and warm inflation, and that's why I'm saying
and it becomes substantial whatever small value of radiation I start with. This is my challenge.
That's right.
Okay, all right.
There will be substantial radiation.
So I thought my code was wrong. Okay.
No, there will be substantial radiation domination, but it will be dominated by your potential energy. Your radiation will not overshoot your potential energy.
Any further quick questions?
Yes.
Thank you for the very nice talk. I have a question regarding the hierarchy of this temperature of the radiation bath versus Hubble scales, because as you say, the phase, the radiation field should not redshift away, otherwise you don't have thermal equilibrium.
That's right. So the difference between cold inflation and warm inflation is that in cold inflation, even if there is some dissipation and you maintain it, so the way you differentiate between cold inflation and warm inflation is in cold inflation H is always greater than T, and in warm inflation T is always greater than H. So your temperature, so this is the hierarchy.
One more question.
Yeah.
Is that in the standard cold inflation picture, we don't, we are interested in computing correlations of, let's say, curvature perturbations, and those remain frozen once they go super horizon. So we don't really care about what happens at the reheating, how the inflaton decays to sand model particles.
Here also the super horizon modes will be frozen.
So why exactly does it matter why exactly does the graceful exit matter? I mean, once it remains frozen super horizon.
No, you have to end inflation at some point of time.
Yeah, but in the context of computing correlations, let's say I'm comparing it to...
No. Even if you're going to perturbation theory and all, you have to end inflation, right?
Yeah, but
so in power law inflation such as you can never do a graceful exit just with a standard mechanism because your epsilon is constant. Even the perturbations are there.
Maybe I'll catch you during coffee.
Yeah, yeah, sure.
Thank you.
All right, let's move on. So let's thank Shratna once again. The next speaker is Richa Arya, and she'll be talking about recent trends in warm inflation.
Good morning, everyone. Am I audible at the back? Okay. So let me begin by thanking the organizers for giving me this opportunity to talk about my work. So I'm going to talk about the recent advances in warm inflation from cosmic microwave background to primordial black hole. And this talk is based on a series of work I have carried out during my PhD, postdoc, and currently I'm pursuing. Okay. So as my previous speaker Suratna has already introduced and motivated warm inflation, so I'll just brush through this slide. But yeah, so some key points about this, the difference between cold and warm is that in cold inflation, the universe attains a supercooled state after this exponential expansion. And there is a separate reheating phase at the end, which then again brings back temperature in the universe. But in warm inflation, there is a production of particles. So throughout this inflationary phase, so inflaton has couplings and it dissipates into these particles throughout this inflationary phase. So you do not require a separate reheating phase at the end. Okay. The equation of motion of inflaton is modified with the additional dissipation term we have already seen in the previous talk. Okay. And this concept was just 15 years after the inception of inflation. Okay. So some of the motivations are already talked about by Suratna. So it's a more, so warm inflation is a general description. Okay. It is more appropriate to consider the couplings. We should not neglect if there are even slight couplings of inflaton with the other fields, that should be considered. So it should not be ad hocly avoided at the first place. Then a reheating phase might not be needed at the end of inflation, that's another point. Then there are certain models of cold inflation, very easy ones like the monomial quartic potentials, which are already ruled out in the cold description, but warm inflation can accommodate those models by lowering this tensor to scalar ratio. Then there are studies which show that warm inflation can also lead to non-Gaussianities. Okay. And in future, if we have some detections of non-Gaussianity, that can be a test of these warm inflationary models. Okay. Then there was a eta problem discussion that the steeper potentials of inflation can also be accommodated in this warm description. So you don't require a very flat potential, even steeper potentials with inflaton coupled with the other fields, that can be also viable with this warm description. Okay. Then there are some conjectures from some high energy theories or UV complete theories, which are Swampline and Transplanckian. I'll talk about it. So even these type of conjectures which can help inflation to embed into some UV complete theory, these are also favorable with the warm inflation models. Okay. And the very important point about warm inflation is that it naturally leads to some features at the small scales which were not explored earlier, but we in our studies have seen that there are some natural mechanisms only that dissipation can lead to the formation of primordial black holes at the very small scales. Okay. So the background dissipation, the background equation of inflaton is modified with this additional friction term, okay, and this upsilon is the dissipation coefficient, which depends on how this inflaton is coupled. Okay. When we can just reparameterize our equation in terms of another parameter q, which is the ratio of the two friction terms. Which one dominates decides which regime of inflation, I mean, if Q is more than 1, we can say it's just a nomenclature to say that the dissipation is more and we are in the strong dissipation regime. And if Q is less than 1, so we are in the weak dissipation regime. And in the limiting case, when Q is 0, we retain what is the standard cold description, the cold inflation. Okay, so how is this epsilon obtained? So it depends on how inflaton couples. So it's solely a function of the field value and temperature, and it depends only on the Lagrangian which we put into while we describe this process of coupling of inflaton. Okay. So there are some motivations of deriving these forms of epsilons in literature. So some common forms are that it's t cube by phi square, it's linearly, so it's only a function of t and phi. Okay. There are different forms which are like they are in, so these two forms are in the supersymmetric inflation models. So we have an inflaton and it is undergoing a two-stage decay mechanism. So it is coupled with some intermediate fields and those fields are then going into radiation. So in the two-stage decay mechanism in these SUSY models, we have two limits, one where we get this t cube by phi square kind of a form and the second where we get a linear kind of a form. Okay. And there is also a warm little inflation model, okay, which is recently proposed in 2016. So extra gauge symmetries are added in the inflaton potential so that the thermal corrections are controlled. Okay. Then there is another form t cube by m square, which is a minimal axion, minimal inflation model where this inflaton is an axion and it has some couplings to the non-abelian gauge fields, and these are recently introduced in 2019. Okay. So the form of primordial power spectrum in warm inflation is modified with the both thermal and quantum fluctuations, and it's given like this. So the first term resembles the standard cold formula we know, and there is additional square term which has contributions because of this T by H, these thermal corrections, thermal noise contribution. Okay. And somebody asked previously that what is the hierarchy of T by H. So this T is always greater than H in warm inflation. So this term is contributing definitely for warm inflation. If you are dealing with a high dissipation, so this is the most dominant one. Okay. Okay. The N represents, so inflaton field itself can be excited from its vacuum state. So there can be a non-zero thermal distribution for inflaton, okay, which is basically this inflaton distribution function, which is considered as a Bose-Einstein distribution. Then the radiation fluctuations can have a feedback in inflaton fluctuations, which can lead to the growth in spectrum, which is encoded with this growth function GQ. It is obtained numerically by solving the coupled inflaton radiation fluctuation equations, and for a linear, it's only a function of temperature, it's independent of phi. So if you have a linear dependence on temperature, the growth is like this, and if it's kind of a cubic dependence, the growth is like this. This is very crucial factor when we are dealing with a strong dissipation regime and when we are dealing at the small scales, because you can see it's a huge power of Q, right? And if Q is a big number, this term is going to dominate a lot. I'll come to it again in next slides. Okay, so in our initial studies, we did CMB analysis of a monomial potential with two forms of epsilons. Okay, and we found that there is a, okay, on the x-axis is the value of this dissipation parameter at the pivot scale. Okay, so pivot scale means the CMB, the 0.05 megaparsec inverse scale. Okay, so we can see that this T cube by phi square can accommodate only a weak dissipation regime to start with. Okay, but a linear T can accommodate both. By accommodation, I mean that this NS is consistent with the the predicted NS of this model is consistent with the Planck results. Okay? So we have both strong and weak dissipation regime possible for a linear T. And the R values, the tensor to scalar ratio values, you can see that depending on the value of Q, we have a lower tensor to scalar ratio. So that means these models can be consistent with the Planck observations. Okay. Okay, so this is how the standard power law parameterization in cold inflation looks, the black line, AS k to the power ns minus 1, that's the standard cold inflationary spectra, and these are the lines which show that in warm inflation, if you have even to begin with a very small dissipation, you can have a sufficiently differing spectrum. Okay. So we see that the inflaton rolls down this potential. To start with, we had a very low value of dissipation parameter, but as inflation proceeds, you see that this parameter increases. Okay. So this is a very crucial point about this model, that it leads to a huge evolution, a huge growth in Q value. Okay. The T cube by phi square and this lambda phi 4 potential with T cube by phi square. It leads to huge enhancement in the value of Q in this inflationary model. Okay. And because the power spectrum I showed is dependent on the growth function, it would be hugely enhanced. Okay. So this is what we explored in our next study, which was on primordial black holes. Okay. So but what are black holes? So primordial black holes are those with primordial origin. Okay. They are different from astrophysical black holes, which are stellar end products. They have different formation mechanism. Okay. They can be formed by collapse of overdensities. They can form very early in the universe, okay, in the radiation era itself. Okay. So there are very, a lot of studies in this primordial black hole after the detection of this LIGO gravitational waves. There is a surge in studies on PBH. Okay. We'll be listening to more of PBH by Rajiv in his talk tomorrow. But okay, so I'm showing here how much abundant black hole can have, like depending on the mass of black hole, its abundance is restricted from various observations. So if there are black holes, why can't we see? So there are different constraints from different observations. Okay. So black holes with less than 10 to the power 15 gram mass, these are bound, their abundance is bound from evaporation constraints, because they would have evaporated by today, whereas 10 to the power 15 grams and higher masses would have implications in gravitational lensing or some other phenomena. So their bounds are from other experiments. But there is this quantity which is basically the fraction of black hole in dark matter. Okay. So if black holes are stable and they are there in the universe, so that they can constitute the dark matter. So there are constraints on their abundance or on their fraction through different experiments. Okay. And there is a window in which there are no constraints to rule them as the total dark matter. Okay. So for the first model, lambda phi 4 and T cube by phi square, when we extrapolated our power spectrum for the small scales, we saw that there is a natural, because the Q is, the dissipation parameter is growing very large, that's why the growth factor is contributing and the power spectrum is getting enhanced naturally. This is not imposed in the potential or in the spectrum itself, it is coming as a natural effect. Okay. This was seen for the first time in this paper. Okay. And the abundance of these, okay, so we see that nearly a kilogram mass, tiny mass black holes are being formed in this model of inflation, and the abundance of these are restricted because of their evaporation constraints. Okay. But if these evaporation ceases at some point, so these are tiny black holes, they are evaporating fast, but if we seize this mechanism at some scale, some Planck scale, then the remnants of these products of these Planck mass can be a dark matter. This is one proposal in a Nature paper by McGibbon. Okay. So we see that possibility here also. Then there are okay, so associated with the scalar perturbations, large scalar perturbations also source the tensor perturbations at second order. Okay, so this leads to a spectrum of scalar induced gravitational waves. Okay, and we see that associated with these tiny black holes, we have a spectrum of gravitational waves of very high frequency. Okay, this is in this work by yeah. So next we explored that whether there is a possibility that we make the dark matter, we obtain tiny black holes, but can we make black holes in the range which is possible for the full dark matter, the unexplored window. So here we considered another model, a non-canonical worm inflation. Okay, we had this additional G type term, worm Higgs G inflation. Okay, so G symmetry is there in this term, and we considered a linear dissipation coefficient. So again we see that there is an enhancement in the power spectrum, but at the intermediate scales, not at the last small scales, but the intermediate scales, which correspond to PBH in this unexplored window. Okay, so we have a possibility that the PBH formed in this model can constitute the total dark matter abundance. Okay. And the associated gravitational wave spectra of these lie in the sensitivity of Lisa, Bibio, Desico. Okay. Then because inflation is a low energy theory, we need to embed it in some UV complete theory, which is done via some conjectures from string theory, which are Swampline and Trans-Planckian conjectures, which favor that we have a sub-Planckian excursion for this. So there are three conjectures: distance, de Sitter, Trans-Planckian. So we require that inflaton evolution is sub-Planckian. Okay, and the slope of this potential is greater, which is not allowed with the cold inflation. Okay, so standard cold inflation is not in agreement with these conjectures. However, we can accommodate these in our worm inflation model. That is what we show here. So because there is a coupling of inflaton with the fields, it can have a sub-Planckian excursion, but still continue to have that 60 e-folds. Even if it starts at a lower value of field and it moves very slowly, it can continue for 60 e-folds to have sub-Planckian excursion, but still attaining that 60 e-folds. The other is basically the steepness of the potential is also, a steeper potential is also allowed in worm inflation. Because it is coupled, so it won't roll down fast. There is a coupling which restricts its motion as a friction term. So it can have a motion on a steeper potential, but still favoring this Swampline conjecture. Okay. Then the third one is Trans-Planckian censorship conjecture, which is related with the scale of inflation, and which is also related with the density scale. Here, this conjecture proposes that the density scale is extremely less. So currently I am pursuing this project, which is with my students, and we are considering again a radical but now we are considering two parallel we see that we can be compatible with the ACT results we can start with a strong dissipation regime, okay, and we can also have a sub-Planckian field excursion. That means Swampland conjectures are also allowed. Okay. So now what would be the PBH signatures of these models is what we are ongoing at present. Okay. So this is the summary of my talk. I leave it for you to read and you can ask questions if there. Thank you.
Thanks, teacher, also for keeping in time. Questions?
Can you go to slide 10, please?
Yeah.
What happens to K? Where is the K end?
Okay, so K end is basically the points here. I mean, whatever model you are considering, this endpoint is the K end. We are exploring the full 50 or 60 E-folds.
What will happen beyond Kn? Have you evaluated the spectrum beyond Kn?
No, beyond Kn, what would it mean? Like,
What do you mean? What it means? I can evolve the spectrum and evaluate it.
No, but that's the smallest scale which is exiting the horizon in
I can
inflationary
evaluate it.
era.
You should do that. Okay, so I will let you do that. You should evaluate. Modes are still there.
Modes are still there, but those who have never exited are never considered. I don't think it's
Exactly. People don't consider it, but you should. Okay, you should examine what happens to them, number one. Because I would like to see what is the nature of the spectrum on those scales.
Okay.
Now, you have used the expression that you had earlier for the power spectrum to arrive at this power spectrum,
yeah.
the analytical one.
Yes.
Typically in cold inflation, such features, strong features will arise. There are slow roll. There are deviations from slow roll. Are there constraints under which your spectrum has been derived, analytical one? Are those constraints valid for such scenarios?
So we are still obeying the slow roll. We are not violating slow roll anywhere. This is inflation with slow roll, but with modified slow roll.
So whether the slow roll parameters themselves are enough, I am not sure when there is an additional field involved.
No, but see,
So
the presence of other fields leads to this Q term. The Q is basically the ratio of epsilon. Epsilon has that interactions with the other fields, right? So the slow roll conditions are modified, like epsilon is not no longer needed to be less than 1. Instead, it can be less than 1 plus Q. So that information is there in the Q. So slow roll conditions are modified considering its couplings.
Because it's often very difficult, you need strong deviations from slow roll in inflation to generate blue spectra.
Yes, that's a difference.
So I was a little surprised in your latest slide that you are unhappy with the red spectra. Okay, we'll talk over coffee.
Yes, sure.
Okay, go ahead, please. So during warm inflation, the radiation must be subdominant with respect to the scalar field, right?
Yes.
So we cannot get the radiation era immediately after the end of inflation. There is some other epoch between inflation and radiation era, right?
It depends on model. So for lambda phi 4 model, if I have it in my paper, if you see that if you evolve rho phi and rho r, there is a mismatch, like rho phi is still dominant at the end. So a little bit phase of reheating might be needed. But there are models, like there are some papers which have some models which like end inflation when rho r takes over rho phi.
So what is the signature of that era on the primordial gravitational waves?
We haven't explored that era. We have just considered inflationary scenario in this study at least.
Okay.
Yeah, that aspect which you are saying is significant, and yeah, that needs to be explored.
Thank you.
Yeah, I have one question. So I always had this question in mind when I had seen your paper. The thing is that you have a flat spectrum for the CMB scales, and suddenly it rises up.
Not suddenly, it took so many E-folds and so many...
but then it rises up,
It
right?
rises up, yes.
But is this a fine tuning?
No, it's not fine tuning.
So then how can you keep us, there should be some upper limit on Q or something that will let your spectrum to be very flat for the CMB scales and then slowly rise up, or whatever is the rate of that
so
rise.
we started with a pivot value of Q.
Yeah.
Then we have a condition that when we can end inflation, the inflation will end when our slow roll parameters are disobeyed. Okay, so we consider eta parameter because that is more in comparison with epsilon. Okay, so we know the end point also from that condition of eta equal to 1 plus q, and eta is basically 1 at 1 plus q, right? We have expression for eta in terms of potential parameters, and this is equal to 1 plus q. This gives a upper bound on q. So we start with a q pivot, we have a q end. In between, it is evolving. It's not fine tuning, it's slow roll only. There is a dq by dn expression, right? You showed
Yes.
in the, so dq by dn governs how this q will go from this point to this end point. Only this dq by dn is enough. There is no other thing required for knowing how it will evolve. And if q evolves, so correspondingly gq will evolve, and correspondingly the power spectrum will evolve.
So I always doubted that it leaves the CMB scales intact. It only affects the scales which are not seen in CMB.
But it's natural process. It's not because q is enhancing.
That I think the physics behind it needs to
That
be
physics
explored.
behind is basically governing the. There is a dq by dn, right? You know, it's not a
Yes.
constant in these models.
That's right.
So,
So
whenever
there are even warm inflationary models where dq by dn decreases.
decreases.
And
right.
then
But
you will not.
this model has an enhancing q, and that is the crucial point why spectrum increases. The other models which have a decreasing q might lead to a suppression in the power. So it is equally possible there can be a suppression for other models where if it is required, we can explore that. But for PBH, we require a high power spectrum value. So this was the motivation to
Okay,
continue
we'll
it.
talk
Sure,
later.
we can talk.
Okay, so I think at the beginning somewhere you mentioned maybe you are saying that temperature is greater than the Hubble parameter. Is this during inflation?
During warm inflation, yes.
How do you make sure the temperature is greater than Hubble parameter? Typically your H square, if the background is thermalized, your energy density is T to the power 4. Now
Yes,
H square
yes.
is T to the power 4. And how your T is greater than H? And
Okay.
how do you maintain that?
Okay, so we don't, okay, yeah, that's a point which is not, okay, so T by H has to be greater than 1 so that these equations hold. Otherwise, there is no point. If this is less than 1, then it's the standard cold stream.
Standard,
Yeah.
yes,
so,
that is my question is how do you get T is greater
so
than
Q
4B?
decides actually for different Q values, the dissipation parameter decides that we achieve that condition.
Yeah, I'm saying say H square is equal to, if it is thermalized, your energy is proportional to the power of background radiation. So, no, but if your H T is greater than H square, T to the power T is greater than H, then your T to the power 4 is always dominating compared to H.
I suggest we continue this very interesting discussion over the coffee. So let's stop here. Let's thank Richa again. The next speaker is Samuel, and he'll be talking about stochastic induced gravitational waves in Palatini FFR gravity. I'll give you warning at 10 minutes for 2 minutes. So we'll do it 12 plus 3. Okay.
Good morning. First of all, I would like to thank the organizers for giving me the chance to present my research. My name is. I didn't select the talks. Yeah, my name is Samuel Sanchez Lopez. I am a postdoctoral fellow here at IMSC, and today I will present this recent paper that I wrote with my collaborator Jose, who is also a postdoctoral fellow in Portugal. This is an outline of my talk. I will first give brief introductions to scalar-induced gravitational waves and to Palatini FFR gravity. Then I will present the main results of our paper, which is basically I can't find the words. We set up a general framework for the study of scalar-induced gravitational waves in FFR gravity. And I will also show some example spectra. And I guess the main point I want to make is that the spectrum of scalar-induced gravitational waves is sensitive to modifications to GR, and these modifications may be tested by upcoming gravitational wave experiments. So to talk about scalar-induced gravitational waves, I have to talk about inflation, but because we've just heard a couple of very nice introductions to inflation, I will just say that it's a period of exponential expansion in the very early universe, which solves the horizon and flatness problems, and which provides a mechanism for the production of perturbations that source all structure in the universe. So I'm talking about perturbations. As you know, the universe on cosmological scales is very large scales, is very homogeneous and isotropic, but there is structure on top of this homogeneity, and the proper language to describe this is cosmological perturbation theory, which basically consists on expanding every quantity that you have, like your metric, your energy momentum tensor, and so on, in a background homogeneous part, plus a perturbation that depends on the coordinates. And for example, this is the most general perturbed FRW metric, where each of these perturbations, A, B, and C, can be expanded as a power series like this. And in cosmology, we usually truncate the series at 2. We usually work at first or second order at most. But the point of this slide is that at any given order in perturbation theory, different kinds of perturbations don't mix. So, for example, here I'm showing the evolution of the gravitational potential and of the gravitational waves. And as you can see, they are decoupled. And here I'm just showing the evolution of this gravitational potential during radiation domination. At superhorizon scales, it's frozen, and this can be connected to the primordial power spectrum from inflation. So at any given order, perturbations don't mix, but if you go to higher orders, you can have sources from lower orders. And in particular, I'm interested in tensor modes at second order, which could be sourced by scalar, vector, or tensor perturbations at first order. But I'm interested in scalars, and this is what scalar-induced gravitational waves are. After some math, you can find that the power spectrum of these gravitational waves is given by this integral, where u and v are momentum variables. You have this factor here, which depends on the polarization of the gravitational waves. You have your kernel function, which encodes the sub-horizon evolution. And you also have here basically the square of the curvature power spectrum from inflation. Actually, the observationally relevant quantity is this density spectrum of gravitational waves, which is related to the power spectrum in this way. And here I'm just showing some examples I took from Inomata and Nakada. For this example, log normal power spectrum, and for example, you can just focus on the blue lines. In dashed, you have the power spectrum, the scalar power spectrum, and in full, you have the associated spectrum for the induced gravitational waves. And why is this interesting? As you know, the power spectrum at C and B scales is constrained. It's about 10 to the minus 9. But at smaller scales, it's not. And in principle, it could be amplified. And if it's amplified, it could lead to the production of primordial black holes. And if so, it would inevitably lead to the production of the associated scalar-induced gravitational waves. And this is hopefully to be measured by upcoming gravitational wave experiments like all of these, LISA, DESIGO, Einstein Telescope, and others in the high frequency range, and the pulsar timing arrays in the nanohertz frequency range. And if this were to be measured, it would provide a lot of information about the inflaton potential at like smaller scales and so on. But again, the point of my talk is that this possibly measurable spectrum is also sensitive to modifications to GR. Okay, so what modifications to GR did we consider? We just considered f of r gravity, which is, as the name itself says, is just a function of the Ricci scalar. And we did it in the Palatini formalism. What is the Palatini formalism? You take the metric and you take the connection and you assume they are independent. This doesn't mean you are introducing new degrees of freedom into your theory, like an extra scalar field or something. It's just a choice of what your degrees of freedom of the theory of gravity are. When you take the equation of motion of your independent connection, you find that it's actually the Levi-Civita connection, the usual connection from GR, plus this correction term here that depends on capital F, which is just the derivative of your initial F with respect to the Ricci scalar. And if you do a little bit more of work and you take the trace of your metric field equations, you find that capital F and therefore also R and therefore also small f are algebraically related to your the matter fields of your theory via the trace of the energy momentum tensor. And for example, for this function here, r plus r squared, you find a similar law as in GR. Now you take all of this and you plug that in your metric field equations, and you find that you get basically your Friedmann equations, and you find extra terms, which are time derivatives of the f function, or in other words, time derivatives of your matter fields. So effectively what this modified gravity does is it introduces additional matter sources to your Friedmann equations. But this is background, at the background level, and we want to do perturbation theory to second order, so we need to do perturbation theory to first order also. And yeah, I will not go into any detail. I just wanted to show that these are the Einstein equations to first order in Palatini f of r gravity. And this is one of the main results of the paper. This is the equation of motion for the second order tensor modes in this Palatini f of r. On the left hand side, this equation is very similar to GR. You just get this modified Hubble parameter. And on the right hand side, your source has the GR terms, which are the first line, and then you get these all other terms, which depend on F and its perturbations, which means that it depends on the matter fields and its perturbations. And this is general, like this is just no approximations are made. But to make progress and to obtain a specific spectrum, we have to choose one F, and we chose one of the most widely used and I guess better motivated examples, which is r plus r squared, Starobinsky inflation. And we studied the production of gravitational waves during radiation domination for W equals 1/3. The trace of the energy momentum tensor for a radiation fluid is 0. So if you go back to your trace equation, you find that the only contribution to the trace is the subdominant matter component during radiation domination. And to give you a taste of how things go, if you look at this capital F, it is 1 plus alpha, the density of matter over m Planck to the 4. This F appears ubiquitously in all the equations, and here basically 1 corresponds to GR, and then you have this modification. So this motivated us to treat, and this is obviously a very small number, so this motivated us to treat the modifications to GR perturbatively. So we expand every field, for example this field here, in its GR plus a modified gravity part, where the perturbative constant is given by alpha times the density of matter at present over n Planck to the 4. And this is a tiny number, 10 to the minus 121 times alpha. So alpha could be huge, and still we're fine in the perturbative expansion. Okay, so we expand every quantity, and in particular we also expand the kernel. And we find that the modified gravity contribution to the kernel is proportional to the GR part times alpha times the temperature overheating squared. And here I'm showing the solution, numerical solution to the kernel. In blue is GR, and in orange is the modified gravity contribution. For alpha equals 10 to the 67, but okay, this is huge, but if you multiply this by 10 to the minus 121, you're still fine. And okay, this is our main result. We computed the spectrum of scalar induced gravitational waves for the same example curvature power spectrum that I showed you before, the log normal law. And in blue is GR, and in orange is R plus R squared. We obtain basically a scale invariant amplification of the spectrum. So for every frequency, you obtain this boost. And what's interesting is that recently this other group, Kugaraja et al., did the same as we did, same setup, everything, except they did it in the metric formalism. And what they find is, again, blue is GR, and in red you have the metric formalism. So GR gives you something, metric formalism gives you something, modified gravity metric formalism gives you something else, and likewise for the Palatini formalism. So hopefully this can be tested in the future by all these gravitational wave experiments. And yeah, thank you for your attention.
Thanks, Samuel, and also for keeping in time. Questions?
Just, but the equations of motion will be the same in either formalism, right?
No, it's totally different theories. First of all, well, I don't have it here.
Why do you say it's a totally different theory? It's the
For
same
two
theory, but you are just restating them in a different fashion, arriving at the equation of motion in a different fashion.
So the reason why the reason why they're completely different is because one way to see it is the trace equation. Here, the matter, sorry, R and F and small f are algebraically related to the matter fields. In the metric formalism, here you have plus Laplacian of big F. So the relation between F and the matter fields is dynamical. So it gives you like completely different evolution.
I understand. So couldn't you have just, you know, during inflation at least converted into, carried out, gone to the Einstein frame and carried out similar exercise?
Yeah, I don't see why not. Yeah.
Then you will get a result more like the other guys.
No, I think our results should be frame independent.
Okay.
Whatever happens to the dynamics that makes it different, I think it carries out, like it translates to the Einstein frame through the couplings to the energy momentum tensor in some way. Like.
Okay, I'll speak to you later.
Sure.
Thank you.
So I have a very nice question. So, so in the affine connection itself, you are adding a new term. So is it guaranteed that for all such scenarios, this scalar vector tensor decomposition theory holds, or there can be theories where the evolution of these different perturbations can be coupled to each other?
So I'm not adding this. This just comes out of just varying the action. The mixing between different types of perturbations, yeah, they're independent. We showed that.
Okay, thanks.
Here.
Just one naive question. For r plus alpha r square, have you checked the Bianchi identity? Because in modified theories of gravity, the Bianchi identity does not hold generally, because for the extra term. In the Einstein
does.
GTR, we have G mu nu equals to T mu nu. So
Yeah.
the Bianchi identity holds for the,
Yes.
if we apply the matter conservation law.
Yes.
But in modified theories of gravity, it does not hold generally.
So I
have you
think
checked that?
in FFR it does, and actually the continuity equation is the same as GR.
Sorry?
The continuity equation, rho dot plus 3h rho plus p, yeah,
Okay.
is the same as in GR.
Okay. And in regard to Sriram question, how can you sure that if we transform the frame to Einstein frame, the gravitational waves spectrum will remain same? I mean, how can you be so sure about that? Okay, we can
I
discuss
think
later.
gravitational waves are conformally invariant, right?
Okay, we can discuss later. no
Sure,
problem,
sure.
Thank you. Yeah.
All right, let's move on. So let's thank Samuel once again. And the last speaker for this session is Divya Chakraborty. And she'll be talking about exploring inflation in string theory, single field versus multi-field models.
Am I audible? Yeah. Hello everyone, good morning. First of all, I would like to thank the organizers for giving me the opportunity to present my work. So today, I am going to talk to you about two single field model of inflation and one multi-field model of inflation. And since the main topic of this session is worm inflation and string theory, let me slowly take you to the string theory domain. So, you know, inflation, so it is a period of accelerated expansion in the early universe, and I am going to embed such such mechanism in string theory. So what do I explicitly mean by that is that I am going to derive the scalar potential driving inflation. I am going to attribute a physical origin to the scalar potential as well as the scalar fields driving the inflation. So both the single field models of inflation that I am going to talk about and the multi-field models, all the scalar fields and the scalar potential, they are going to have a physical origin derived from string theory. And my talk is going to be based on these papers and are done in collaboration with these people. Okay, let's begin. So, I mean, in my talk, the three papers that I am going to present, the three works that I am going to talk about, in all of them, there will be some things that are going to be common, which are the string theory model building, which is telling you that how am I going to derive the scalar potential and what are my scalar fields. More or less, the physical origin to the scalar fields are going to be also the same. But if they differ, I will let you know. And the moduli stabilization, because when I say string theory, usually what comes to the mind immediately is that there will be a lot of scalar fields, right? Because string theory comes with a lot of extra dimension, and once your dimension reduce, you get a plethora of scalar fields. So you have to stabilize the extra scalar fields. So I am going to talk about inflations, right? So my inflation is going to be the leading order flat direction. But the leading order flat direction, but the leading order stabilized directions, they need to be stabilized. They need to stay stabilized even at the level of 4D, otherwise they will mediate fifth force. So my, so when I talk about string theory, I have to let you know what will be my extra dimensional topology, because the derivation of the scalar potential as well as what exactly are the scalar fields, they will depend on this topological structure. So for my case, this topological structure is a K3 fibered Calabi-Yau, which is nothing but a two-dimensional base, and which is like a disk, and on each point on that disk there is a K3 fibered K3 fibration. So there is a two complex dimensional manifold sandwiched on this disk. And when I talk about this volume inflation and fiber inflation, they are single field models of inflation. And in those cases for volume inflation, this whole 6-dimensional volume will stretch and expand in its space time and will give us the period of accelerated expansion. When I talk about fiber inflation, this vibration, so this fiber is going to stretch and expand. And when I am going to talk about multifield inflation, a combination of these scalar fields, so there will be 3 scalar fields that will appear. The combination of them will stretch and expand, and there will be some kind of assisted inflation. So, I haven't checked yet, but maybe the single field models will not work when I talk about multifield inflation. So, there will be an assisted inflationary kind of picture will emerge. Okay, so slow roll inflation in its minimalistic situation is when a scalar field, minimally coupled scalar field, minimally coupled scalar field slowly rolls down a potential, and as soon as it stays in this plateau region, inflation takes place, and once it rolls down, inflation stops, and one usually takes care of all these how long the inflation is taking place by these slow roll parameters, and as soon as they hit 1, inflation stops. But and this is also the we all know this is the Planck contour plots, and all this colored region that you can see, these curves, they are they are based on various single field models of inflation, and we can see that they are well within the Planck window of observation and within the Planck contours. But then why do we need to go beyond that? So in order to answer that, we need to know that other than particle physics, for cosmology, you should not take gravity as a constant. You should not work on a static gravity domain. So you have to take the dynamics of gravity into picture, and since inflation happens in such a high energy scale, the quantum gravity constraints might also become important, and for string theory being the leading candidate of quantum gravity, we might be interested in working in that domain, and hence the subject string cosmology has emerged, and I am going to talk about string inflation in that. Okay, and not only that, so string theory naturally features these scalar fields which can drive this accelerated expansion, inflation, and also it can also give rise to dark energy, quintic scalar. Okay, and many others. So and these are the things that we have to keep in mind, like why do we need to go beyond the single field model of inflation and the toy model of inflation? What is the motivation to go beyond? Okay. So now the outline of my talk is the following. So first I would like to search for the de Sitter vacuum, because we know we have to, in cold inflation, we have to reheat the universe. So the field has to go through the oscillation. So we need a de Sitter vacuum to start with, and if found, then I would like to examine what will be the inflationary implications of those vacua that I am going to find. And one thing that I should already tell you is that I am going to talk to you about because I said that I am going to derive the scalar potential, right? So the way I am going to derive the scalar potential are based on only the perturbative corrections from string theory. Because usually, you have, I don't know if you have heard about this LVS and KKLT type construction, which is the famous de Sitter construction found in the literature for string theory vacuum. So now I'm going to go slightly beyond that, and I'm going to just work on perturbative corrections, because perturbative corrections are well understood from the 10D perspective, and non-perturbative effects are not. So it is, I'm going to claim that it is better than the LVS and the KKLT scenarios that were studied earlier. Okay, so this is a busy slide, but the takeaway from this slide is the following. So I'm going to, I'm talking about superstring theory, right? So I'm starting from 10 dimension. I'm dimensionally reducing to 4D. So whatever is happening in my 10D is going to be carried forward to 4D with the help of this standard Guko-Vafa-Witten superpotential and the Kähler potential. And remember that these are tree level. Tree level means this is the simplest interaction that could happen in the Lagrangian, right? So this Guko-Vafa-Witten superpotential, this omega and G3 that we are seeing here, those are actually taking care of all the fluxes that are needed to stabilize this extra scalar fields that I was talking about. And this is also taking care of, this is also carrying the information about the geometry. So I'm already carrying forward the information from the extra dimension. And the scalar potential again, but there is a different combination, but the scalar potential is also taking care of the same thing. So the volume is taking care of like how my geometry is embedded, like whether I am talking about this K3 5 Calabi-Yau or some torus or whatever. So now I don't know if you remember that in the start of my talk I said my inflatants, the inflatants are leading order flat direction. So in this leading, so these are these leading order corrections, right? So in the leading order correction, just these leading order corrections are not sufficient to stabilize the inflator. And this is helpful in a way that because since this is leading order flat direction, they are usually less massive and easier to inflate with. Okay, and the main point of this slide is that these two potential, I mean this super potential and the scalar potential helps us to derive our scalar potential to drive the inflation. Okay. So I keep talking about inflation because that is the main goal of my talk, but I mean this is just usually used to stabilize the scalar fields as well. So it can be used to do many other things as well. Okay. So now I have to stabilize the inflatants because those are leading order flat directions, so I have to stabilize those flat direction using this set of corrections that I am going to consider. So these are all perturbative corrections. So those perturbative corrections appear in two series in the 10-dimensional string perturbation. So one is in the string length and the other is in the string coupling. Okay. Now if we add the standard alpha prime cube correction, that is the first leading order corrections in the string length, and the higher derivative corrections, which is the second order string theory corrections, string length correction, then I arrive at this potential which we have shown, this is the potential which is simpler looking, and it is single field where my phi is the scalar field which is also the inflator, and all these constants they can be written in terms of several other parameters, and I get these questions quite a lot that it looks like there is a like array of parameters, but it is not so. So once so this W0 and GS are my main free parameters, and once I fix this GS and W0, the other parameters will be based on that. So I cannot choose arbitrary numbers, I cannot just throw arbitrary numbers to them. Okay. So and once we plot plot this potential, and once in the this is the zoomed in version of the of this side, yes, okay, and we can see that it features a nice flat plateau to sustain inflation, and we have also checked its this is by the way this is the volume inflation I am showing, and in the volume inflation we have checked the volume, it's a large volume scenario at the end of the day to to keep the perturbative corrections under control. This is a well known things in string theory. And we have also checked the power spectrum, the spectral tilt, spectral index, and and one main thing and one beautiful feature of this model is that this volume inflation, this is the first single field model I am showing, is that this is a small field model. Hence it is okay with the light bound and as well as with the Swampland conjecture, so Swampland distance conjecture to be precise. And so this is the next single field model that I am going to present now, is that this is the fiber inflation, but fiber inflation in using only perturbative corrections. So in this scenario, since we do not have any non-perturbative effects, what beautiful things that it brings is that there is no scalar cone bound. So usually these fiber inflationary models, they suffer with a problem where the inflaton, how much it can, like field excursion is bounded by scalar cone conditions. But since there is no non-perturbative effects, there is no such bound in this scenario. Since I have only 2 minutes, I will skim through. And again we have checked the inflationary regime and we are okay with that. Let me show to you the last model, which is a 3-field model, which was the last work that I have done on this perturbative large volume scenario type situation. Okay, so this is a 3-field model of inflation, and in all the 3 fields, they are the base, the overall volume, and the K3 fiber Calabi-Yau. So, in this situation, we have added the log loop correction and the leading order alpha prime, the leading order alpha prime cube correction, the log loop correction, and the another leading order, subleading order, sorry, subleading order f to the power 4 correction. And we have stabilized all the direction, and this is the one of the most important feature is that the second slow roll parameter, there is a violation, there is a brief violation of slow roll, and it returns back to slow roll again. So, there is a violation of slow roll, and we can confirm that. So, these type of features usually gives rise to an enhancement in the power spectrum, and which might be useful to study the prime order black holes as well as the secondary induced gravitational waves. So, there could be interesting features, and not only that, it can also be used to study the non-Gaussianity, because usually we have also checked the turning rate and the torsion in this 3-field models of inflation, and usually because of the presence of these turns and torsions, they have non-trivial effect on the non-Gaussianity as well. It has been found. And how long do I have? 1 minute? Okay, 0. Okay, so I'll just stop here. Okay, so yeah, so I'll just stop. I'll just let you read the thing. Thank you.
Thanks, Divya. Questions?
So, in one of the models you showed these parameters which fit the data very well. If you can just go back even more. The previous one. Yeah, this one. So, you really have to fine tune your model parameters so much to fit the models. So, because you have taken so many numbers after.
Yes, yeah, this is also another question I get very often. So, this is what I get after I plug in some value. So, this is not the fine tuning. So, suppose I give some numbers in the Mathematica, and then the Mathematica gives those the Mathematica gives those orders of magnitude, and I just put it there. So, from the next talk onwards, I really should remove those. So, I don't need to fine tune that. So,
Okay.
suppose there's like this R2.
It looks like a very fine tuned
Yeah, so no, they are not fine tuned. So, fine tuning, I will say, so this W0 being 0.038 is fine tuning. I need exactly 038, maybe 39 will give something. It will not overshoot my model, but it will give some other prediction. Then my lambda being 10 to the minus 4, this is what I need. And CW being 10 to the minus 5, 10 to the minus 5, this is what I need. The rest of it, what I get from Mathematica, for instance.
Okay.
Yeah.
Any other questions? So I thought the upshot is that if you want to be consistent with the observations, this is the very specific set of parameters that will work with the observations, right?
Yeah.
Which
so
means there is a fine tuning.
So fine tuning in the sense, in the paper, so here I am just showing, I just picked the best parameters, set of parameters. So in the paper you have actually given a range of parameters.
Okay.
It's like where
So there's a wider range of parameters.
Yeah, there's
which
a
is all
wide range of
consistent with
parameters.
it.
Yeah, even in the 3-field model. So you can imagine, so even this 3-field model, so I'll just answer what I could not say in the talk. So this, this brief violation of slow roll is actually occurring because there is a global minimum. And when the the 3 fields are away from that global minimum, the third field, which is like the dominant one during the first period of inflation. So you can see that these are the 1, 2, 3. So these are the 3 fields where the first field is the most dominant one in the first period of inflation, and the 2 of them are slowly moving. So when this one is going here and it's slowly oscillating, it's because the 2 of them are away from the minimum and there is a ridge being formed, and this field which is dominant in the first period, it falls in that ridge and oscillates, and that oscillation actually induces this brief violation of slow roll. And once the other 2 fields goes close to the global minimum, this all of the fields find their global minimum and they go to their global minimum, and I mean it comes back to the normal slow roll, and the inflation ends when all of them are at the minimum. And this feature is retained for a wide range of parameters, but even since this is a string theory model, one has to make sure there are various scales and there are various parameters we have to make sure, because there are supergravity approximations, there are various no-go theorems.
I think I got your point, yeah. Sorry. So if there are no more questions, let's thank Divya and all the other speakers of this session. And we are running a little behind schedule, so we will reconvene at 11:45 after the coffee break.
Hello. Can you hear? Okay. Ah. Astronomy, astrophysics, and space engineering. Ah, yeah, yeah. Oh. It looks like a dasi, means yeah, it's not a, it's a
Okay, so let's start the next session on reionization. First speaker is Prakash Gaikwad from IIT Indore. Please.
Yeah, thank you. So I would like to thank organizer and Dheeraj for two reasons. The first reason is of course inviting me. The second reason is keeping my talk just after the tea break so that people will feel energetic. They will need it in my talk most probably, towards the end at least. Okay. So I'm going to talk about reionization, and since this is the first talk in the session, so I'm going to give a brief introduction. So we know that after the epoch of recombination, in universe entered into dark phases, and then the first dark phase is supposed to be ended when we have the reionization because of the first stars and galaxies form. So there are three main important questions about reionization. Those we want to ask. The first is, what are the sources of reionization? What is the nature of reionization? And what is the timing of reionization? Now, the other problem that I'm going to talk about today is what makes the reionization a most challenging problem. And here I'm going to argue that the real problem of reionization is not about ionizing photons, but about understanding the recombinations. In order to understand that, let us consider a tail of 3 photons, and let us assume that these 3 photons originate from the same star. Okay? And I'm going to show you a very realistic image of or a representation of a galaxy now, in which the star is embedded into the interstellar medium. Okay? So now, the first photon is actually emitted from the star and get absorbed by the interstellar medium. We know that the interstellar medium is highly neutral and very dense. So as a result, the photons will ionize the atom. But then, because of the high density, there is a very finite probability of recombination, and through the electron cascading, you emit the lower and lower energy photons. As a result, the photons will get, the neutral atoms will get, the ionized species will get recombined very fast in the interstellar medium. And this is what we call as a recombination happening within the interstellar medium. The second one is one of the photon actually escapes the influence of the galaxy and goes to the intergalactic medium. It ionizes the gas in the intergalactic medium. But we know that the density of the gas in the intergalactic medium is very high. There is a finite probability of and this is and the third photon goes even past the and goes to a very, very large and the speed what happens is that so as a result, the interior as a recombination happening with the cell. So we have 3 different kinds of recombination. The second is IgM, and the other is this is actually highly uncertain. And as it is a customary in astronomy, if it is highly uncertain, we associate a 3 parameters with understand the ISM recombinations very well. This is usually parameterized by escape fraction. When we don't understand about the IgM recombinations, we talk about the clumping factor. And we also don't understand about the Lyman limit systems, how they are distributed in the universe. We typically associate a mean free path, how much a distance a photon will travel before getting absorbed. Okay. Now, the definition of mean free path that I told you about the Lyman limit systems that it traces is actually valid for only post-reionization phase, when the reionization has been done. But during the reionization, mean free path is actually sensitive to the neutral fraction. Okay. In order to illustrate that, let me now show you the maps of neutral fraction for 3 different simulations that I have run. So in this case, you can see that the neutral fraction is slightly larger. Here neutral fraction is less and it's highly less. And if I compute the mean free path for these 3 models, I get around 3.2 H inverse co-moving megaparsec, slightly higher and higher. So mean free path is actually depends on the clumping factor. Okay. Now that's what I want to claim. So first of all, if the clumping factor is large in the intergalactic medium, the recombinations would be large. If the recombinations are large, neutral fraction will be large. If the neutral fraction is large, the mean free path will be shorter. That's what you see over here from this one. And this is very nicely illustrated in the paper by Tirth very recently, that the mean free path is inversely proportional to clumping factor to some order. The other reason is that if you have a large clumping factor and you have a larger neutral fraction, you have to ionize the universe by redshift of 5.3, that is indicated by the Lyman alpha forest. So in order to ionize that, you need ionizing photons, so they should escape the influence of the galaxy, so your escape fraction has to increase. So all these 3 recombination processes during the reionization are highly coupled to each other. So what can we do about the observation? Of course, escape fraction is very hard to, nearly impossible to measure directly at very high redshift. Clumping factor, because it's a diffuse radiation coming from the intergalactic medium, so it's also very hard. And also it's very hard to model because the dynamic range needed for the clumping factor to model is huge. But what we can do is we can try to measure the mean free path. Of course, measuring the mean free path is also hard, but still we can manage to do that. So here is what I'm going to do about how we measure the mean free path in the universe. So what we typically do is we typically do the measurement of the mean free path using the Lyman continuum profile fitting. So we observe some quasars between redshift and Z to Z plus delta Z. You stack the spectrum, all the spectrum together at rest frame wavelength of 912 angstrom. 912 corresponds to hydrogen ionizing frequency, 13.6 electron volt. This is what typically you get when you do. So you can see the typical profile at 3.4 and this is at 4.0 stacked from different quasar spectra. This is from DAISY DR1, and you fit an exponential profile model. Now, in order to fit that, you also know that the quasar is a high intensity radiation source. So we have to take out the contribution from the quasar. We also have to take the contribution from the foreground. So when you do that, you get mean free path, constraint on the mean free path. And this method really works very well if the mean free path in the intergalactic medium is much larger than the quasar proximity zone sizes. Okay. So this is going to be the most important plot in my talk. What I'm showing here is the mean free path as a function of redshift, the evolution of the mean free path as a function of redshift. When we do this kind of Lyman alpha profile fitting, Lyman continuum profile fitting, what we see is that there are measurements of the mean free path, something going like this. You can very well fit with the power law using a uniform UV background model. What it means is that all the universe gets ionized at the same time, and then you get something like this, a power law kind of fitting. Now, in the recent year, what we have been trying to do is trying to extend this measurement to higher and higher redshift. And this is what George Baker has done in 2021. He did a measurement at 5.1, which is actually extremely good agreement with the power law. But when you go to a higher redshift, it starts to decrease, the mean free path starts to decrease. As I mentioned earlier, mean free path depends on the patchiness of the reionization. So this was kind of expected, so there is no problem with that. The problem happens because the mean free path also is sensitive to the patchiness of the neutral fraction. So you can ask the question, this will also have imprints on the Lyman alpha forest. Instead of Lyman continuum, you now go to the Lyman alpha forest. If you take the opacity of the different regions and plot the cumulative distribution function, what you see is that the short mean free path corresponds to more scatter, a long mean free path corresponds to less scatter. So you can use this information to constrain the mean free path. So now you have measurements from Lyman continuum profile and you have from the Lyman alpha forest. So this was the state from the Lyman continuum profile. When you have the Lyman alpha forest, you see a decrease. Okay, so as expected from the uniform U background. The problem is here. The two measurements from Lyman continuum and Lyman alpha forest, they are actually in 1.2 sigma tension with each other. Now, we thought that, okay, this might be due to the fact that we have a less number of samples. So let us increase the number of samples and see whether we get the same result or not. So in 2023, led by the same group, but the PhD student Yongda Zhu, they did the same analysis. And what they found is that the mean free path is actually very well consistent with the Lyman alpha forest up to 5.5, but suddenly it is actually decreasing with the redshift at 6.0. And in order to explain these things, we turn to the simulations and ask the question whether the simulations can produce this. So we have two kinds of simulation. One is called Eton and Thiessen. What they do is they are calibrated to match the Lyman alpha forest. When we try to match the Lyman alpha forest, we are not able to match the short mean free path. There is another kind of simulation, cosmic dawn 3 simulation, which actually produces short mean free path. But when you look at the effective optical depth distribution, they do not even match. Okay, so you can match either one of them, either Lyman alpha forest or Lyman continuum profile at redshift greater than 6. Now, this is known as a short mean free path problem in the literature, and this is quite old, like 4 years old problem. Now, you can ask a question, this is just a 1.2 sigma, why should we care? But this is actually misleading because we are talking about the mean free path, but if you convert it into a neutral fraction, there could be a very, very big differences between the two models. The other thing is that because the mean free path is short, the ionizing photon budget has to increase very, very drastically because of this. And in this case, since the reionization is happening very quickly, it has to be very, very rapid and very late, which might be inconsistent with the JWST results that we have. And of course, even if it is 1.2 sigma, this does not discourage IGM community to tell about it could be a new missing physics or something, so they can always claim that this could be a more clumpy IGM or there could be a delayed hydrodynamical response. Okay. So in order to make a progress, what we thought is that we started with doing a new analysis of the Lyman continuum profile fitting. So our approach is not about the fitting, the Lyman alpha line, Lyman continuum profile, but rather to forward model everything and compare the forward model directly with the observations. So here I am showing you two slices. One is correspond to a light cone of short mean free path. This is a long mean free path. You put quasars at the location of halos and extract the long skewers. Okay. Then because we are looking at the quasar proximity region, so you solve 1D radiative transfer along the line of sight. And then you also do the detailed foreground modeling because the Lyman series is actually a foreground. So we do the full forward modeling and then account for observational systematics like resolution and finite signal to noise ratio or so. So here I am going to show you a sample of some profiles, the stack profile at 5.1. So the green one that you see over here is from observation, and one of the forward model Lyman continuum profile from our simulation is shown by the red curve. So it looks okay. Okay, so I have not done any fitting here yet as of now. So we vary parameters that are related to the quasar properties, for example spectral indices or age of the quasar. What we find is that there is a mild variation with the age of the quasar. But when you vary the mean free path actually changes the profile quite drastically. And this is a signal to noise ratio variation, so it's a bit, so it happens, it matters to the constraints that we get for the signal to noise ratio. So now I'm going to show you the constraints that we get from the mean free path. So this is what is plotted on the y-axis is the chi-square, plain chi-square, no reduced, but the degrees of freedom for my analysis is 11. So you can also get the goodness of fit if you look at the plot. And on the x-axis is the mean free path. This is what I'm getting now. So you can clearly see a minimum that is happening, and you can see this demarcation line that is there is roughly 1 sigma for this analysis. So if on this plot, if I plot the Lyman continuum profile measurements from the Yongda Zhu, what we see is that systematically our best fit values are actually larger as compared to the mean free path that has been measured by the other people using the simple exponential profile. On the same plot, if we plot the Lyman alpha forest, the measurements coming from the Lyman alpha forest, they are actually consistent with the Lyman alpha forest very well. I'm going to show you now the best fit value, how the best fit model looks like when we look at the stacked spectrum. So this is again flux at four different redshift bins. This is the observed value. The points here I'm showing you just for the convenience of stacked profile, the bin one. And these are the best fit models. So all these models are, there are 100 models for 100 mocks for single model. And you can see that the black points and the red points, they are very well with each other. If I take the Yongda-Zhu's points, the Lyman continuum profile, you can see that at the 1.2 sigma, we can actually rule out that measurement very clearly. Okay. So in this plot that we have, the mean free path, previous mean free path model, this was the situation. When we looked at using the new measurements, what we see is that this is consistent with the Lyman alpha forest very well. So what we claim is that there is no short mean free path problem. It's just you need to forward model carefully because the mean free path of the IGM is not as short as, not as long as compared to the quasar proximity region. So you have to do a full forward modeling of ray tracing and radiative transfer. And this is my final summary of my talk, where what I said is that understanding recombination process is the main challenge. The mean free path is actually one of the parameter of which is related to recombination that we can actually measure. And mean free path happens to be very short in the literature, but when we compare with the full forward modeling, we see that it is consistent with the Lyman continuum profile. And all of these results actually suggest that the reionization is rather ending late. We don't know when it is starting, but we at least know that it's ending late. Thank you. I'll take questions now.
Thanks for finishing actually early.
Thank you.
Yeah, so Prakash, just to understand what exactly you did, so basically you will put a quasar proximity zone and then...
no, I will not put proximity zone. I will put a property of the quasar and then solve the radiative transfer.
So you will put an n dot and a TQ.
N dot TQ, then I will have a spectral indices and all other things.
But where did they go? Are they included in the error bar here?
I mean,
because there's an uncertainty there.
Yeah. So I included them. So that's why I did not mention it. But when I show this chi-square, it is actually like a marginalized likelihood. So I took into account that thing.
And
mean free path is free parameter, but I also have TQ, slight dependence on TQ. So that is IGM, correct.
Yeah. And
sorry? No, I want to measure mean free path. I get error from here.
And what is the radiative transfer scheme you are using here?
Okay, so just a one-dimensional radiative transfer. So you just integrate along the line of sight. So the boxes that I am telling short mean free path, those are using Excite ray tracing code because I already have them. No, UVB will change. Okay, so. Gamma H1 is consistent with the ionized fraction that I get, photoionization rate that I measure at these redshifts within the bubble. But outside the bubble, forest, exactly. That's correct. Yes. Yeah. Where to look? Okay.
Thank you for a nice talk. So you have said that the evidence suggests late reionization depending on the MFP, but what about clumping factor and escape fraction? There are still uncertainties. Whether that, if we get more information about those two quantities, will this conclusion change?
Okay, so clumping factor or escape fraction, okay. So this is a bit complicated question. So when we say mean free, we say in reionization is ending late. What we mean is that in order to explain the observations, we need a patchy reionization. That means fluctuations in the neutral fraction. That means that means the reionization has not been completed yet. Just based on that information, we are saying that it is late. The clumping factor and escape fraction, of course, they are very, very difficult to measure. So one of the thing that I did not mention about this result is that one of the authors from the Fred Davis has actually tried to constrain the clumping factor using this kind of method, the mean free path method. So when they use short mean free path, they get the clumping factor of 20. That means you get very, very high recombination. If that happens, then your escape fraction has to go very, very high. But because now there is no short mean free path problem now, so you will have a relaxation. So typically the clumping factor we are talking about is 3 to 5. This is a globally average quantity, 3 to 5, okay? But if you look at Thiel's paper, I mean, he will know better, you have to have a conditional probability of densities in order to get the local clumping factor. So these are slightly different things. And regarding escape fraction, I'm as ignorant as you are, so I don't know.
Thank you.
Yeah.
Okay.
Yes,
Hi,
yes.
Prakash. Thanks for the nice talk.
Mhm.
This is more of an implication of this thing, if there any. So there was this paper by Villesana et al. Which hinted at a 4.5 kb warm dark matter.
Yes.
Do these understandings change any of those results?
No, I don't think so, because those are done using the Lyman alpha forest,
Yes.
first of all, and those are done at low redshift range 4 to 5, where the reionization has been already over.
I thought they had some data points beyond 5 also, if I remember correctly. But maybe not at this.
No,
Okay,
no,
fine.
no.
So
Yeah.
this doesn't change?
This doesn't change, no.
change
And
the
I am ultimately showing this is consistent with Lyman alpha forest, so it will not change.
Yeah, that's true. Okay, thank you.
Yeah, no worries.
Hi, Prakash. Thanks for a nice talk. I have two questions. One is on the, when you put the quasars and halos of different masses, how do you do a selection? Because there may be a halo mass dependent reionization fraction or escape fraction. So how do you take into account that or analysis?
Correct.
And
So
the
first
second
of-
question will be on KZ, because you already have bounds from kinematic Sunyaev Zeldovich effect from CMB on the weight and kind of the epoch of mid-reionization. How that agrees with these measurements?
Okay. Yeah. So regarding your first question, how do I put the quasars, first of all, okay? So first of all, we have a completeness limit of our sample for halo mass function. So we typically put above 10 raised to 9 and 10 populates with halo. Now, I do not have an escape fraction as a free parameter in my model at all. I just assume that they just radiate and then they get the mean free path. So I am interested in the what mean free path they carve out. So escape fraction naturally, if I have to calculate it from my thing, if the mean free path is short, my escape fraction will automatically be reduced. But I'm not interested in at least tuning my parameter. Yes.
And is this quantity halo mass dependent, the mean free path?
No, it depends on the clustering of the halos. Because when you say the reionization is going on, what happens is that it's the property of how the halos are clustered that drives the reionization. Individual halos will not have any contribution. And I do have a plot, may not be here, but I can show you that it depends on the clustering
Because
of
the
the halos.
gas fraction will decide in the halo. If there are more clumpiness or gas fraction, the amount of photon that can actually come to IgM is less.
Correct. Yes.
That will have an impact.
Correct. True.
We can talk about this.
Yes.
What about the KSZ part?
KSZ part, okay, I'm not much expert on KSZ part, but what I can tell is that the models that I showed, they are ending, so they have a late ending reionization. I cannot tell anything about the midpoint of reionization. So what happens is that even if the midpoint of reionization at say 7 or 7.5, it does not matter for the Lyman alpha forest because it is ending
Already
very
in low
less.
ratio.
And the neutral fractions that I'm talking about here is less than 0.1. Lyman alpha is a resonant transition, so it's a bit complicated to say. Yeah.
Okay. Any more questions? No? So let's thank
Thank you.
Prakash again. Next speaker is Raghunath Khara from ISR Kolkata.
Okay, let me start by thanking the organizer for giving me this opportunity to present my work here. What I wanted to discuss is the present status of this 21 centimeter signal observations and what we have learned so far. So I will skip the basic introduction of this probe because that was already been discussed yesterday, and we'll directly start with this light cone of differential brightness temperature. Now, this is a simulated light cone. X-axis is the redshift, y-axis is the angular direction. And this is created using this 1D radio transfer code Graceful, which I had written during my PhD. Now, you see the features, all these combinations of positive and negative regions and also the positive and zero signal regions. These are due to the presence of sources, and three radiations are mostly important when we talk about this 21 centimeter signal. Those are Lyman alpha photon, and X-ray photons and UV photons, right? So why this particular probe is very interesting and important is because this is a line emission, means whatever region in redshift we want to observe, these are some way connected to our redshift observation. You just choose your frequency of your observation, you just choose your frequency, and that will probe what exactly state of universe you want to probe, right? Already several observations are going on, and LOFAR, MWA, HERA are producing results. NANOFAR, it is probing little bit high redshift, but still it is producing interesting result. ARTFAC is stopped now, and SK will come very soon. Now, these are interferometric observation. That means they are trying to probe the fluctuations of this signal as a function of linear different length scales, right? Of course, this thing we have listened yesterday as well, that this particular probe is very challenging as the strength of this signal is very small compared to the astrophysical foregrounds, and it's very difficult to basically extract the signal from this hugely foreground dominated map, which we will finally observe using our radio observations. There are also complications from instrument side, but if we are doing our calibration methods like very accurately, and if we prepare our foreground mitigation process very perfectly, then if we go for a long integration time, then it is possible to basically recover the signal which we are looking for, and this is like the hope, and this is basically the point what all the observations are taking and doing this observation. Now on, I will be basically talking about this LOFAR. This is for an example. Let's say this is a radio interferometer trying to observe this NCF field. So what they observe is this visibility in radio data, and they choose different frequency band, and this is a typical pipeline they follow for processing their data. Now they basically remove the RFIs, they do calibrations, prepare a sky model to basically mitigate the point sources and extended radio sources from their data, do some averaging, then they subtract the diffuse foreground part using, they apply a GPR based method and recover the signal plus noise and prepare the power spectrum of this signal. Now this team LOFAR, they are trying to basically mitigate the foregrounds, they are not using the wedge. For example, like Samir yesterday talked about this applying the UR wedge to recovering the signal, but this team particularly is trying to basically mitigate the foregrounds and recover the signal. Now you see that this is after they do the direction dependent calibration. In this map they have signal, noise and diffuse foreground part, while you see that this red region is like strong foreground contribution. Then they apply this GPR based foreground mitigation method and derive up to this level of signal plus noise. For an ideal case, this is supposed to be a signal plus noise thing, but there are still some systematic left, and as you can see that some region the signal to this ratio is above 1, which is saying that still some systematics are left, but what the point is that for this particular plot I am showing the recent LOFAR results at 3 redshift bin, like this is at 10, 9 and 8, and they are prepared the upper limits on the differential brightness temperature dimensionless power spectra using this 140 hours of observation. These are upper limits that we have to keep in mind. These are not detection, means the signal is somewhere below this value, right? So here whatever like the fluctuation levels are, these are signal plus noise and let's say remaining some systematic. Now the thing is whether these upper limits are still useful to get some information about UR or not. So if I state the current status of this field, that is highlighted by this particular figure, x-axis is the redshift, and there are so many observations are already putting upper limits. This dotted and dashed curves are the let's say theoretical predictions for standard scenarios, and the upper limits are here. you can see that the best upper limit is from this Hera observation. LOFAR is also producing very good upper limits at redshift 9 and 10. At high redshift, NanoFAR is also being very promising, and their upper limits are going down day by day. Only the thing is like they have to integrate, like all these observations have to integrate more observation hour to reach to this level. There at some point there will be saturation, and some this observation will claim for an detection. So these are like the status from this interferometer based observations. Now the point is like, okay, still with these observations or upper limits, we can rule out some model or not. What we learn about the EOR. So this is the context of this talk. So when I am talking about inference, two things are mostly focused. One is like the properties of sources, because the signal, the strength of signal is mostly, let's say, determined by what type of sources are there, how many sources are there in that particular region which we are probing. So this particular source property inference is most of the focus of many teams. In addition to this, I also try to focus on this IEM properties, means like if I am not that much interested in the source properties, but just ask this question, how big these ionized regions are, right? I am just avoiding the question like, okay, what is the emissivity, but just I am interested in the size of these ionized regions. So these are something related to the intergalactic medium properties. Now a typical inference framework looks like this. So we use a code here, like for this LOFAR team, we use this Graceful code, which I just discussed previously. That is working under like this source parameter, which are ionization efficiency, minimum mass of UV emitting halos, minimum mass of X-ray emitting halos, and X-ray efficiency. Now, for a combination of this parameter, Graceful will produce a map like this, right? For that, we will produce the observable. In this term, these are the power spectra, and then we will basically couple that with the observed one through a likelihood. And this is the basically Bayesian framework which we use. Now, as I am also interested in the IEM quantities, so I also consider these parameters which are related to the intergalactic medium properties, which are ionization fraction, heated fraction, means like the fraction of regions with the temperature more than the CME temperature, mean gas temperature, and I use a mean free path method to characterize the size distribution of, let's say, the emission regions, and characterize the distribution in these two parameters, which is R peak and the full width of at half full width at half maxima. This one are the parameters which characterize the distribution which we derive from this mean free path method. Now, talking about this LOFAR results, the upper limits are here, and this is like 1 sigma error bar. So what we do is that we explore our source parameter space, and here I am presenting like 1000 models randomly chosen from this entire set, and trying to see if any model is above this upper limit or not. What we see is that only tiny bit of models are actually above the 1 sigma level, and these models which are presented in color, that has higher probability to be ruled out. Okay, so only like the models which are above, let's say here, these are ruled out, we can say, by 1 sigma level. Now these are like only 5 to 10% in total set which we use. It's not very good at this stage. So for that, what we try to do is study the statistics of this excluded model or disfavored model. Scenario is the same when we go for the other two redshifts. These are redshift 8.3 and 10.1. And when we do a Bayesian analysis, then the results are presented here. So what we found is that the disfavored model, and these are without any radio background or something like that, these are pointing towards very highly patchy reionization scenarios or highly patchy heating scenarios. These are pointing that disfavored model prefers high emissivity from the sources, high UV emissivity, and their number densities has been very small. That is highlighted by this high value of M min. This is also true for these X-ray properties, which will lead to very patchy heating scenarios. For example, here I am presenting two slices from two excluded scenarios. Here the yellow regions are ionized regions and these green regions are neutral regions without any heating. So this is a very patchy ionization scenario, and that will produce a power spectrum which is much larger compared to the upper limit. And this is a scenario which is ruled out. And this is a patchy heating scenario where the yellow regions are now positive signal and this is negative signal. This is also ruled out by this 1 sigma label from LOFAR. Now this same Bayesian analysis also put limits on these IgM parameters, and this is more or less 2 sigma level of limits which we derive. What it says is that ruled out models are very much like it will have huge ionized regions or huge emission regions, and those are only set of very extreme models which at this moment can be ruled out. Now when we also incorporate all possible upper limits, whatever we have from this 21 centimeter observation, what we found is that okay, at recip 8 it is basically biased by Hera observations, and it is ruling out a model which is this dashed line which present neutral and cold IgM at recip 8, which is indicating that at recip 8 IgM has to be heated in some way, right? And this is also been true at recip 10. This is roughly touching this limit, but it's not I mean possible to rule out at recip 9, but at recip 10 it is ruled out. So this scenario is already ruled out at recip 9. Now apart from this interferometer based observation, there are observations using single antennas, and for example this AJS, LEDA, SARAS, which are trying to observe the sky average signal as a function of redshift, and it has been shown that several models has been ruled out already. And for example, we use AJS high band data, not the low band. Low band data is the least controversial data, but still using the high band data which doesn't claim a detection, we are able to rule out for example a fuzzy dark matter type of model, right? Now AJS low band data, which is created this controversial brightness temperature profile, which has a very strong signal, and its nature of this profile is also very different compared to what theoretical predictions are, and that deep signal can be only explained introducing excess cooling mechanism or excess radio background. But it is probably that their analysis method was had some error, and it's probably due to some residual unmodeled systematic which led to this particular very strong signal. So this is more or less understanding at this point. Now apart from that, SK is on the way, and there are huge amount of theoretical studies in terms of let's say imaging topology study, detecting large ionized regions using matte filtering techniques, bispectrum maps, etc., which is giving us very high hope that okay, over down the line in few years, so we will have very good quality of data, and various very precise science can be done with this SK data. And it's already like in a timeline frame, there are already like 4 antennas on ground, and in few years there will be this A2 configuration with 64 antennas, and we will have some data to start exploring, and over few years of course we will be able to do much more. Also there are updates from other observation side. For example, there are many space-based instruments planned. From India side there is Pratus planned, and there are already from your side DARE, DAPPER and far side been planned, and if that is happening, let's say in 10 years or so, which will give us advantage of let's say avoiding some systematic, and which will lead us to a better achieving let's say the goal in terms of let's say both power spectra as well in terms of the brightness temperature average quantity. Now with this I will just summarize what I tried to convey here is that this 21 centimeter probe is a very promising, as this is line emission, and we can just probe different state of universe at different era. Already the results from LOFAR, Hera and FWA, they are ruling out models, and they are progressing very nicely over last few years, and these are moving towards a detection which will probably happen in, let's say in next few years. So there is a huge improvement in understanding the systematic in different team, which is going very nicely. So what I talked about is the inference about the source properties and the IGM properties. What I tried to say is that at receipt 8, 9 and 10, so there presence of the patchy reionization model and patchy heating model, this is not the scenario at those redshift. Also, these limits are anyway very weak, so most of the models are still valid, and we will be waiting for the let's say the upcoming telescopes, and those will provide us very nice information. So this is the hope. So I'll stop and.
Hi, Ru, a very nice talk. So I just wanted to ask, when you calculate power spectrum using your Grizzly simulation, do you also consider the fact that, so your IGM is very, very cold, and that will raise the H1 optical depth. So the assumption that optical depth may be small may not be true. So do you consider
so
that?
For this 2025 study, we did that, but in 2020 study, so that was one thing, we were using the linear expression for tau. Here only one thing is missing, that we still are not including the light cone effect. So okay. That will be like, okay, taking more time. We are including the resistive distortion in our study, but not the light cone effect. Otherwise, the tau thing is incorporated correctly.
Okay. Thank you.
In the couple of models you say ruled out, what does it say about the sources at redshift 8 or 7 or something? It tells something about particular sources cannot have some F escape or something, or what?
Yeah, so these sources are having like huge emissivity in UV. So in principle, like if you use a luminosity function type of thing, those models are already ruled out from there. But this is like, okay, already towards that line and independently verified by H1 observation.
Hi, thank you for the very nice talk. I have a naive question. So in the Grizzly, you have two of the inputs are the minimum halo mass for the UV emission and the X-ray emitting halos. So is it ever possible to, from these values, if there is a measurement ever, to pull out the POP3 star mass function or the AGN mass function, or is it too computationally expensive to do it? I know there are other uncertainties that will come in, like escape from days, there are all of these things.
This is possible. So it is our plan, and we are developing a new code, new version of Grizzly in polar, which is basically tracking all the evolution of, let's say, the halo mass function as well as the luminosity function, or like from the star level. So there, all these things have been done consistently. So there, of course, like the number of models will be ruled out, probably will be less, because here I have the freedom that, okay, I can choose any emissivity, etc., etc. But when we do that, so there will be already a constant from there. But
it's in that case, what is the maximum value of the POP3 mass that you can take? Do you know?
Okay, that hasn't been studied, so okay. That we have to check.
Okay, thank you very much. Thanks.
Okay, no more questions. Let's thank our speaker again. The next speaker is Khankar Muhammad Asif Ilahi from IIT Madras.
Hello everyone, I hope I'm audible. Thanks very much for giving me this opportunity, and I will straight away start with where Raghu finished, I think, and Shambi introduced some of these things yesterday. So I will talk about observing this 21 centimeter signal from the epoch of reionization using one of the very powerful telescope, the Murchison Wildfield Array. So let me begin with this statement that we are in an exciting time where we are detecting the tangential symmetric signal in the post-UR region. The telescopes such as CHIME, Meerkat, which has already detected the signal with very high significance, either directly or with cross correlation with galaxies. And as Raghu shared, that we are in a time where we are making very deep upper limits, where we can start ruling out models of epoch of the reionization. And we are now improving on those things. So my talk will be on how we process the data, how we remove the foregrounds, how we deal with some of the systematics, particularly focusing on this telescope, the Murchison Wide Field Array, which is a precursor to SKA, and very similar things is expected to happen with the square kilometer array. So this is a plot of the bandpass of the MWA telescope. So this is a frequency axis, and this is the response of the telescope at different frequencies. And you can see this peculiar structure in the bandpass, which comes because you cannot correlate so many antennas at the same time with very high resolution and frequency. So you have to have some kind of you cannot sample the signal at a very high resolution for the entire antenna, for all the antenna, and you end up having this kind of features in the bandpass. And this is the actual data that we measure from where we want to measure the tangential symmetric signal. So the x-axis shows the frequency, and y-axis arbitrarily shows the measured visibilities, amplitude of the visibilities. So the measurements are called visibilities. What we measure in interferometer is called the visibilities. And you can see these gaps every 1.2, after every 1.28 megahertz there is a gap which comes from the bandpass of the MWA. This is from actual observation carried out using the telescope, and the data has been described in this paper. What happens when you do the estimate and power spectrum from this data is this. So this is K perpendicular, it tells you about the angular scale, and this is K parallel, this tells you about the frequency or the line of sight in this case. So you see the lower K parallel regions are dominated by foregrounds. These are very strong signals, and these signals is repeated in the higher K parallel. So typically what we expect is that the foreground will be limited to this region, some wedge region, and this region will be free for you to do your studies, but this is not the case when you have such kind of bad band pass. So how do you deal with that? So there are these regions from where you can measure the power spectrum, put upper limits, but then you have these contaminants, and then your limits are not good enough. And this is the same pattern you will see in all the MWA power spectrum papers that is there in the literature. What we do, we take an alternative approach. We do not take a direct Fourier transform of the visibilities along the frequency. Rather, we measure this quantity CL delta nu, which is the 2-point correlation along frequency plus the assumption that the signal is ergodic along frequency. So what matters is the separation between the two frequency, not the individual frequency. So you can first do a 2-point correlation and then do a Fourier transform to get the power spectrum. And it is shown in the simulations that even with flagging and no flagging, these are the same flagging as the MWA data has, but you cannot distinguish with, you can recover the signal in this method, and there is no such abrupt features in the power spectrum. So simulation shows that this works, and this is the result from the actual data, and I will come to this plot again and again, and you can compare that in this plot which directly Fourier transform the visibilities along frequency, you will see this kind of reoccurring foregrounds at higher K parallel. This is not the case here. But if you look at very carefully, this is also not quite free from the foregrounds. These are at least 3 to 4 orders of magnitude smaller than the highest value, which is improvement, but then there are these ripples. The problem with this is that if you integrate over time, these ripples will not go away. The noise will go down, but these ripples will stay. So you have to figure out some way to mitigate those ripples. So this is the problem that is the main focus of this work. And so we investigated why these ripples are coming. Even so, our idea is that in this kind of estimator where you estimate CL delta nu, we shouldn't see the ripples, but still you find these ripples. And we finally found out that, I will not go into those very details because that will not be very much interesting to all of you. But what turns out that this assumption that the signal is ergodic holds to some extent for the 21 centimeter signal, but it doesn't hold for the foregrounds. And so this kind of ripples appears when you have a data, when you use data that have foregrounds, but doesn't appear when you have signal. So what do you do? So this is first, the first thing is that we understood this, where this problem is coming from, and then this is an explanation of the same thing, that an ergodic signal, this is the frequency axis and this is the frequency separation axis. So an ergodic signal look very similar along the frequency axis, which is not the case here because the data is foreground dominated, and there are other structures in the data due to the instrument. But this is the problem, that we are averaging over this direction, assuming that the signal is ergodic, but because the signal has mostly dominated by foreground, this assumption doesn't hold, and those tiny ripples comes up in your final power spectrum. So we proposed a new method to deal with this. The idea is that if you can remove the foregrounds, or at least the amplitude, you can reduce the amplitude of the foregrounds, and you can reduce the spectral behavior of the foreground to some extent, then you can mitigate those ripples. So let's see if that happens in the case of real data or not. So what we did is that we tried to find out the smooth part of the data. So we did some kind of windowing using a hand window. There are many other methods. We found that this works very well. So we use this hand window to find the smooth part of the data, and then subtracted the smooth part. And I will show that there will be no signal loss beyond the smoothing scale, and anything that is less than the smoothing scale, we will not use that. So this will be a hybrid approach where you will remove some of the foregrounds and then avoid those regions to constrain your signal. So this is what the values will look like. The signal now will look like mostly ergodic, and then now we are in a position to average this signal to get a power spectrum which we expect to be like this, and this is what we get from the actual data. So this is the main plot that the main result of our work. This one is before the smooth component filtering. You see that as I said, that the power is much lower than the lower k parallel values, but now we can see this is much more cleaner, and we are now in a position to check whether this is consistent with noise or not, or can we constrain the 21 centimeter signal using it. This region is excluded in our analysis because we have filtered the smooth part of the data, so this region doesn't concern us. We are not using this region. This is the same method. So one of the questions that we have been asked for many times, that did we try our methods on simulated data and run it through the whole pipeline? Yes, we do. We do it routinely. So this is a 22 centimeter simulated 22 centimeter signal that goes through the entire pipeline, that is making the visibilities, running foreground removal, filtering out the smooth part, and you can see that in this region this is very similar before and after the smooth component filtering. If you estimate the power spectrum, you will see that beyond the smoothing scale, this matches very well with the input EOR model. So our method works. This is the final result. This is the power spectra, the spherically average power spectra that we get before this smooth component filtering, and after filtering out the smooth part, we are very much consistent with the noise, and this is a very around 2 orders of magnitude improvement from without this SCF method. We didn't stop there. We tried to see if these values are actually consistent with noise, so we compared it with noise simulations and found that this is very much very much consistent with noise. There are some excess variance of a factor of around 1.4, but this is very negligible if you compare with before SCF thing, and this is consistent with the statistical fluctuation within 2 sigma. So all the analysis has been shown with only one pointing center. So I didn't describe about what the data, what the observations are, so now I will come to that. So this was a drift scan observation where the telescope is sitting at one place, the sky drifts over over it, and we have only analyzed only one pointing center. From that we have got a very deep upper limit, Now we have 163 of such observations, and Shovik has done this huge task of analyzing power spectrum for all the pointing centers, and he has found upper limits on all the values for all the whole entire RA range that can be probed by the MWA. So one thing we can see is that the power is very much, the upper limits are very well constrained in these regions, but not in these regions, and that is mostly because of this 4NAX-A source that comes into the side lobes of the MWA telescope, and also the diffused emission that comes into the side lobe of the telescope. So we decided to only focus on these regions. We wanted to combine the power spectra from these regions, and we found this combined power spectra after this smooth component filtering, and found this kind of pretty much Gaussian-like behavior of the noise statistics. So we are very much confident that this is consistent with noise. And in the upper limits, so these are the upper limits with only one pointing center, that is 17 minutes of data, and with the entire diff scan observation, 6.2 hours of data, we got an upper limit of this. And you can compare with the approach where one directly does a Fourier transform along the frequency. The upper limits are, the upper limits from 110 hours are very similar to the upper limits that we got from 17 minutes. But the problem is that because we are filtering out some of the smooth part of the data, we are not able to probe the low K value. So this is some of the drawbacks of these methods, that you cannot access the largest scales. But this is still very much improvement than a traditional method of directly Fourier transforming. That is all from that. We now need more data points to add and go down in the upper domain limit. Next, I will show some preliminary results from the same data. Using the same data, we want to measure the EUR. Can we measure the EUR bispectrum? This work is led by the PhD student Sukhdeep, and this is the formalism is very similar. Instead of doing a 2-point correlation, you are doing a 3-point correlation now to get the angular bispectrum. And I will show some results from some specific triangle configurations. These are very preliminary results. We got report yesterday actually, and they are very promising. And these are some of the measured multi-frequency angular bispectrum. And these are, since the data is foreground dominated, the bispectra is the bispectra of the foregrounds, not the signal. And there are some, we see that for different triangles, the foregrounds, the correlation of the foregrounds are slightly different, but we are not, I mean, we are just presenting the results. We don't know the actual interpretation of what is happening there. And this is the bispectrum. So once we do get the multi-frequency angular bispectrum, we can do a 2D Fourier transform to get the EUR bispectrum. And one question that comes is that where is the wedge? So the wedge is a little bit complicated here. So in this axis I am showing the K2 parallel. So now, right now, in power spectrum we had only K perpendicular and K parallel. We now have K1, K2 perpendicular and parallel, and 3 K perpendicular. And it is difficult to show it, but this K2 parallel is shown here and K1 parallel is here, and the EUR window are somewhere in these regions, and it depends on what kind of triangle you are measuring and what kind of triangle shapes you are considering. But if you show it in a slightly different way, this looks very similar to a power spectral results. And more details we can discuss later. And we have used this to put upper limits on the 21 centimeter bispectrum. This is one of the first studies to get upper limits on the 21 centimeter bispectrum. These are pretty high than the expected 21 centimeter signal, but these are very preliminary. So I hope Raghu will at some point we use this upper limit to put more tighter constant on the IGM parameters. And this has been done for all the triangle shapes. So this is a summary. Don't do a direct Fourier transform. Estimate the maps, then do a Fourier transform. That's the first message. The second is that even if you do that, you will see very tiny ripples, and you should do some method to filter out the foregrounds, which we call the SCF, but we seek better methods for this. And we have put very tight constraints from only 17 minutes of data, and we are in the process of improving it. I have shown some preliminary results which shows very deep upper limits, and we have put first upper limits on the 21 centimeter bispectrum. So that's all.
Okay, thank you. Questions?
you showed the power spectrum curve with SCF. So in that plot, what explains the reduction in the error bar at high K?
Right.
Yeah.
Right, this one, right?
Yes.
Yeah, so the error bars in the measured CL delta nu or the maps depends on the amplitude. Since we have removed the smooth part, the amplitude part of the data, so the error bars also decreases. So
that is the low K part, right?
Yeah, it depends on the overall amplitude.
Okay, thank you.
Yeah. Yeah. So as if this wedge you talked about in the bispectrum, is this the theoretical wedge you're talking about, or whatever you see from the data? By theoretical wedge, I mean this horizon limit, what you do for.
Yeah, so this is the theoretical line.
So this is obtained from that whatever visibility formula.
Yeah, so there is a formula that it depends on, there is a, so this is a linear, so there is a direct formula from between K perpendicular and K parallel from where you get this horizon line. So it depends, so it is the horizon of the telescope, that's it. So this is the theoretical line and this is the wedge that we get.
Okay, more questions? No, then let's thank.
Thank you.
And last speaker is, no, so one speaker is missing. So the next speaker or last speaker of this session is Ranit Behera from IUCAA.
Yeah, hello everyone. I'd like to thank the organizers for the opportunity to present my work, giving me the opportunity to present my work. So I'll talk about these hydro simulations we are running since the last year, and briefly about the light synthesis process and our results. This is done with the supervision of Professor Raghunath Srianand and with collaboration of Nishikant Khandai, Professor Nishikant from Niger, and Professor Prakash Gaikwad from IIT Indore. And these simulations are aimed at producing the first set of galaxies in cosmic dawn. And there are some big questions in this period which people are asking. And we want to explore whether the conditions under which these galaxies formed and evolved and affected their environment, is it similar to the present local universe or is it different? And since now we have observational data from ZWST, we can compare the results, and if needed we can improve our understanding. Now what ZWST observes is, you can observe the spectrum, which is a little bit expensive, or you can observe the photometry points and you can fit a spectrum. Now what you observe is the UV to optical band in the rest frame, and there are various spectral features from which you can infer a lot about the source and its environment. What I will focus on is the UV luminosity, which is how bright the source is at 1500 angstrom. And this actually tells about the instantaneous star formation rate over the galactic time scale. And for local universe, there is actually very well calibrated relation which tells you star formation rate given the UV luminosity. The other one is ultraviolet slope. So what you do is you fit a power law in this range from 1500 to 2600 angstrom, and the power law index is called UV slope because in log-log plot it is a straight line. And these two actually fit the normalization and shape of the spectra, and when you observe a lot of galaxy, you can study their distribution the distribution of UV luminosity is studied using something called luminosity function, where you just bin various observed luminosity in different brightness bins and normalize it to volume, and that is the luminosity function. And UV slope, you can study the scatter plot or something. Okay, so like for past decade, what people have been doing, so they have been running simulations and they have calibrated the UV luminosity function in the present like local universe, redshift around 0. There are also semi-analytic models, and also people have like the observed luminosity function, they have calibrated it how it evolves with redshift. Now when they extrapolate it to very high redshift, it doesn't work. That's what the initial early results suggested, as you have seen here, 2022. And now we also have like spectroscopic confirmation, and we see still that there is some not like the data is not agreeing. So this is the typical situation. You have observational point and theoretical prediction, and they are not matching. So, and people have been addressing this from all directions. Observationally, what they are doing, we want to reduce this error. So to account for the cosmic variance, you can look for various directions and do large volume survey. You can do spectroscopic confirmation and reduce the contamination, and accurate photometric data reduction. And for some sources, this is actually helpful, like they do come this side. On the other side, you can like theoretical side from cosmology and galaxy formation, and at high redshift they are actually related. From cosmological side, you want to push this upward by forming more number of galaxies, and you can do it this with blue tilted power spectrums and non-Gaussianity. I'll not talk about that. What we are interested in is galaxy formation. So push this curve this way, that is to form more brighter galaxies. And reality might be something in between, we don't know. But in the galaxy formation, there are a lot of uncertainties, and like since the beginning people are suggesting various this analytic model, and they have explored these models, how it is helping this like this thing. But all of these effects are very much coupled in galaxy formation. And to correctly account for this coupling, simulations are very powerful. They account for all the nonlinear physics and coupling between them. And but these simulations are very expensive. If you run it to redshift 0, it takes about 6 months or something. But we have an advantage because we are analyzing our data at high redshift. We only need to simulate for 1 billion year compared to 13 billion years. So that is 10 times less time. So we can play with more parameters and check more things. So we do simulations. So this is an overview of how these simulations are set up. You start with a homogeneous distribution of particles, dark matter and baryons. And then at your starting redshift, your initial conditions, your starting redshift, you generate a power spectrum using Boltzmann called class. And then you offset these particles, this small perturbation from linear theory. It gives small position offset and sets the velocity of the particle consistent with the power spectrum. And once your IC is generated, the gravity is standard n-body core, and for the gas particle we have all these cooling physics included in our core in SPH formalism. As a result of that, this gas particle, it condenses into the central region and its density increases. And at certain point the ISM is like when the density is increased enough, the ISM is treated with subgrid manner. And after certain point, when the over density of our gas particle crosses some threshold density, we switch on the star formation for our baryon particles. The stars are formed stochastically in a probabilistic manner over multiple generations, and when stars are formed, they give supernova wind feedback to its neighboring particle, wind feedback and stellar feedback like hitting them, and the metal return. We also have black hole formation criteria and the related feedback in our simulations, but I'll not talk about the black hole because they are not very effective, at least the model we have till now, they are not very effective at high redshift in terms of that they have not accreted enough mass, so the feedback is not enough there. So this is, okay, so we have run this hydrodynamic simulations with the code called MPGadget, it's publicly available with Planck 18 cosmology. And here you see how all these blue points, okay, we call our simulations ninja by the way. These top 3 points, these are run at Ayuka, and all these bottom points they are run at Niger Bhubaneswar. And this is how it compares it like very popular other simulations. They are all aimed at a different goal. Some are like with little bit older cosmology. Older cosmology. And our model closely matches with this asteroid simulation, which is sitting there. The best resolution we have is for the baryon mass. We have is 2 times 10⁵ solar mass, which is sitting here. So this side is best resolution. That will resolve your subgrid physics better. But you see, this resolution is like comparable or even better than like Millennium TNG, but they have 10 times more volume, which is needed to probe those very large massive galaxies. But because of limited computational resource, what we do is we run multiple boxes and we stitch like different boxes probe different mass range, and there are techniques to stitch these boxes and probe a larger dynamic range, which is what we do. And this is one of the picture we have for this 50 MPC 1008 cube particle at redshift 0.5. You can see the dark matter field, gas field, stars field. Black holes I have not shown, zoomed in picture here. However, just because at lower redshift the structures are more visible. However, my analysis today I will present that will be for above redshift 7. Yeah, so before going to light generation, we want to make sure that our structure formation is okay. So here we see the something called dark matter halo mass function. This is just similar to luminosity function, where instead of counting the brightness in various bins, you count the mass in various bins. And we see that for various resolution of our boxes, they are on top of each other, which is a good thing because you want to make sure your results doesn't depend on your resolution. This is good for dark matter. Also for the gas particle, that is also pretty much well conversed. But for star and gas metal mass, you see small deviation, which is coming because of the resolution effect. And then there are techniques. Yeah. So here I have shown the dark matter mass to stellar mass relation, and you can see that they are not a perfect straight line. Although there is a linear correlation because of this resolution effect, they are not matching. And then there are techniques to correct for this mismatch between resolution. And when we correct, we see that the agreement is better. It's subtle, but it's there. And here we have shown the other two plots which are relevant for my talk. One is galactic main sequence, that is the correlation between stellar mass and star formation rate. And we see that like one of the observation is going through all of our points. This edges you see because of various boxes we have put here and some cut we have put here. There is gas metal mass to stellar mass correlation, which you see is a very well defined correlation that is present on a simulation, which will be relevant for my talk in some later slides. Yeah, now we want to generate light from these things if we want to compare with observation. So first thing is the intrinsic and nebular light. So what we do is we take BPAS spectrum. I'll just explain it briefly, our light generation. So we have templates from BPAS, which actually takes into account the binary fraction in galaxies. That's the standard what people are using nowadays. And all these templates, they have very much flexibility in terms of they give us like 9 IMFs, various S bins, 13 metallicity bins from primordial to 2 times solar, and spectral cover is very good. And we pass these templates to cloudy photoionization code and get the templates for like nebular emission. And here what I have shown, so if you see the mass resolution we have, it is like 10 to the power 6 solar mass or 10 to the power 5 solar mass for the best we have. So when you say one star particle in a simulation, physically it is actually a star cluster. So the light one single star particle generates in our simulation, that is actually something called single stellar population, where all the stars are of same age. And what BPAS provides us is the same SSP synthesis. And here I have seen one of the example of the intrinsic light and the template from the cloudy photoionization code. You see the effect of including the nebular emission is to change the slope a little bit. It will affect our result. And yeah, so that is for one single star, but our galaxy have lot of stars. We'll see like 10,000, 30,000 stars. So what we do is for all of our stars carry their age, metallicity and mass. So based on those information, we pick the appropriate templates and we add them. We correctly scale for the mass because BPAS provides us for 10 to the 6 solar mass. Yeah, so that is how we generate the intrinsic light. But we know that a little bit of dust will affect a lot, a lot to the light, and modeling dust is difficult. That's why everybody does it differently. What we did is we start with a simple scaling law that people observe the visual extinction. Visual extinction is the like the intrinsic light and the dust suppressed light, the difference between them in the visual band, you call that the visual extinction, V band. And there are different techniques, people observe visual extinction and total hydrogen column density, not the neutral one, total hydrogen column density. And they find a correlation between those two quantities, and you also expect it from the theoretical grounds. And these are, by the way, points from the Milky Way galaxy with supernova remnants, planetary nebulas, X-ray binaries. But when we apply it to all the other galaxies, we have to account for the metallicity, different metallicity different galaxies have, which is scaled with a power law here. And so this term, this relation between visual like AV to NH, that is there, we scale for the power law, and these two terms becomes the metal column. And then we apply a first factor, the kappa is this factor which is coming from here. Then we account for a first factor to account for the variations at the like cosmic down, early universe case. Yeah, so here you see that if we can find the metal column density, we will directly tell the AV and we can then use it. So, and finding metal column density is straightforward. From every star we shoot a sight line, and at various points we probe the nearby gas particle, gather the SPH contribution, that will give us the metal column density at a single point, and then we just integrate it, that will give us the total column density for a star. Okay, so so I'll go first then. So that is the straightforward, but what we have, we can either shoot sight line from the central, like every galaxy is a central star, that the potential minimum, we can find the intrinsic light and apply one single attenuation load to the whole galaxy, that is called central attenuation, or we can shoot the sight line from every star particle, that is actually more accurate, and we see that this every star particle shooting, that gives us visual attenuation which is more close to the observation. And yeah, and this is so this is what we are doing. We are independently modeling the SED, which we plan to then. So we want to mimic the observers. We will feed it to the SED recovery, so like bagpipes, for example, which feed the SED. We can pass there because our generation is independent. We can check if like different SED software, they assume different star formation history, so whether that has any effect on our relation. We can also, because we are generating the column density, we can also find the neutral hydrogen column density, and we can generate the DLA here, as you have seen here. We generate band pass photometry at various ZWST bands. We can generate image. The pixel we match with ZWST. We add the noise given from the ZWST sensitivity. We convolve with the PSF, and because we didn't run any halo finder, we can actually use source extractor to find the sources, and if there are various halos linked by a filament, we will find it there. So now I will directly go to the results. Here what I have shown is the luminosity function at redshift 7, and we see that it goes through all the the agreement is good, and here it is missing 2 points. First of all, this side some of them are Asian contaminated, and above this range they are mostly Asian, and here you can see the difference between the intrinsic light and the dust attenuated side, the impedance of dust, and this faint end side you see that they are not affected by dust, which is also shown here. So you see this is the relation between intrinsic and attenuated magnitude. You see that at faint end there is basically no effect of dust. At high end there is a upturn which is seen in our data, and this is also seen at blue tides, which is actually like precursor to asteroid, our closest model. And this happens because when you have more bright galaxy that is coming from more star will also result more metal mass, which will produce more dust and hence more dust attenuation. And because this faint, so yeah, you see this side, because of this large AV, they will their column density is more than 21 centimeter square. They will totally block this neutral hydrogen, totally block the UV ionizing photon. So what we see is that our models show that the reionization is mostly driven by the faint end galaxies. This luminosity. Yeah, it is not changed. This model is for Savrier IMF with epsilon 3. These are what we have taken. I will see what happens when you change this thing. Here what we have done is, so there is different attenuation laws people use. Three of the most famous, cited ones at high redshift are Kaljiti for starburst galaxies. Gordon, which is standard for low metallicity galaxies, and something which people inform from supernova, because they say that high redshift stars don't have enough time, dust doesn't have like this SGV star dust formation channel, the stars doesn't have enough time to go off from the main sequence. So this is mostly informed from supernova, and the law is basically what this attenuation law, it takes from AV to AUV, and different attenuation law will give you different suppression and also change the slope. What we saw is that different attenuation law does change here. We can see two lines because two of them match here, so one is on behind of another. And in the bright end we see that this is suppressed, it's on from here, but this can again fixed with this epsilon. But in the faint end side we see that there is no effect from the dust model. We can also see there is the epsilon here. So what is epsilon? Is the first factor, and so this basically goes. Different epsilon basically relates to different grain size distribution and different composition, and we see that it is between 2 to 3. We have not done chi-square fitting or maximum likelihood now, which we plan to do very soon, and we can see that all of them still go through the faint end, but bright end, but not the faint end. So this end actually can be useful to, this is not affected by dust, so this can be used to probe IMF effect and effect of star formation efficiency. Here we have shown for the IMF. So IMF basically gives you the distribution of various stellar mass in the mass range in a cluster. We can discuss this later since I have less time. And we see that top heavy IMF, which has more massive star, that produces a little bit bright light compared to bottom heavy. And this faint end side is now affected. It is a little bit good, but still it's not passing through this thing. So this results can be used to constrain the IMF effect, but brighter end there is still degeneracy. Yeah, I'll just stop up. So this is our result at various other redshift. This is showing the star. So the effect of different star formation efficiencies. So we have some model to enhance star formation efficiency with weak wind. We can explain it later. You can see it is there and different morphology coming from different models. This is the same galaxy. This is how constant dark matter mass to light ratio and other results basically compared to our light synthesis model. And one other thing is the UV slope, which we are still doing this thing. This is so this is the UV slope and how it's compares to observation for various attenuation law. And as I said, in the bright end there are lots of degeneracy. So this will be like you see Kaljit and SMC, one is going top, one is going through. So this will be helpful to break that degeneracy. As you can see here, one of the curve is going better through the observation, and in our future work we can tell about this thing.
Thank you. We can have maybe one question.
Yes.
Hi, Ranit. Very nice talk. Couple of questions. I have only one question to ask, so I'll list them now. So I'll wrap it up. How do you model the star formation rate evolution with redshift? And given the fact that the supernova feedback will depend upon the stellar mass, so do you, depending on the change in the IMF, how do you regulate the supernova rate?
Yeah.
But there are more questions here lastly.
Yeah, I missed this because of time limits. So one thing is, how do you model the star formation density? That is self-consistently modeled in the simulation from all the feedback. Second thing is the effect of IMF on star formation rate density. That is not modeled in the simulation now. So that improvement is needed from the simulation side. Only the metal return in the simulation depends on the IMF, which is actually takes the Savrier 300 IMF. It does also depend, which is not modeled there. So those improvements are needed from that side.
One more question. Okay, Ranjan.
Hi, thanks for the very nice talk. I have a question. In your simulations, do you resolve individual galaxies? Because JWST has measurements of the stellar radius.
Yeah, you can see, right?
Half-light radius, right?
So I have one picture actually. Yeah, so here you can, this is one of our galaxy.
So does your half-light radius match with what, say the JWST measures?
So, yeah, this is one of our plan. In our future work, we will measure the morphology distribution, and this will affect from various models which we also plan to run in the future. So this is one of our future work to run various models, morphology study, calibration. These are one of our study which we will do.
Okay, thank you very much. Thanks.
Yeah, but the radius is in the ballpark is correct now, but lots of calibration needs to be done because the software we want to exactly mimic the observers. We want to run the source extractor, Galfit with observers too. And they have a lots of parameters, those software themselves, so a little bit calibration is needed. Yeah.
Okay, thanks. So let's thank Ranit and all the speakers of this session.